permitting the light from this line and from no other portion of the spectrum to pass through the second slit to a photographic plate. If the plate be moved at the same speed with which the solar image passes across the first slit, an image of the prominence will be recorded upon it. The same method answers for the study of the sunspots and other features of the sun's surface. As the result of telescopic, spectroscopic, and spectroheliographic observation, it is now known that the sun's principal features are its sunspots, its photosphere, its chromosphere, and its corona. A sunspot, when examined through a telescope, consists of a dark central region called the umbra, into which long, narrow filaments reach. The space occupied by these filaments is termed the penumbra. The darkness of the umbra is not absolute, but is relative to the more brilliant surface of the photosphere, and if observed alone, would be far more brilliant than the most powerful arc light. These dark spots on the sun were familiar objects in the days of pre-telescopic observation, but their importance to astronomy dates with their discovery in 1610 by Galileo with his telescope. The great Italian astronomer did not announce his discovery until May 1612, by which time sunspots had been seen independently by Thomas Harriot, 1560 to 1621, John Fabricius, 1587 to 1615, who published his observations in June 1611, or before Galileo, and the Jesuit father Christopher Scheiner, 1575 to 1650, all of them pioneer observers with the telescope. End of section 11. Section 12 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 9, The Sun, Part 2. Before sunspots were clearly observed with the telescope, it was assumed that they were due to the transit of Mercury. Even Father Scheiner, after his telescopic studies, suggested that the spots might be small planets revolving around the sun and appearing as dark objects whenever they passed between the sun and the observer. It was recognized, however, that the spots appeared to move across the face of the sun from the eastern to the western side, or roughly from left to right. Father Scheiner's view was also held by Jean Tarde, canon of Sarlat, by Father Malpertius, a Belgian Jesuit, and later by William Gascoigne, the inventor of the micrometer. Galileo, however, advanced a cloud theory, while Simon Marius, astronomer and physician to the brother Margraves of Brandenburg, proposed the ingenious slag theory, according to which the dark spots were the cindery refuse of a great solar conflagration, and occasionally expelled in the form of comets, which afterward blazed up with renewed vigor. Galileo, in a controversy with Father Scheiner, proved him wrong in his planetary theory, while the occurrence of the comets in 1618 won supporters for the theory of Marius. Galileo also ascertained the rotation of the sun in a period of between 25 and 26 days, as well as the general zone of the sunspots. The next important contribution to sunspot theory came from Durham, whose observations were made during the years 1703 to 1711. He believed that the spots on the sun were caused by the action of some new volcano, whose smoke and other opacious matter produced the spots. As they decayed, they became half-shadows encircling the darker portions and finally became bright spots. Lalande, the celebrated French astronomer, believed that the spots were rocky elevations, about which the penumbra represented shoals or sandbanks, while around flowed enormous oceans. Lalande's explanation, as well as that of Durham, was clearly based upon terrestrial analogies, which were employed with considerable frequency by early astronomers. In 1769, Alexander Wilson of Glasgow, 1714 to 1786, examining the large sunspot visible that year, noted that as the sun's rotation carries a spot across its disk, there was a change in its appearance, and that the same effect of perspective was produced as if it were a saucer-shaped depression, the bottom forming the umbra, or central black spot, and the sloping sides the penumbra, or surrounding portion of half-shadow. The penumbra appeared narrowest on the side nearest the center of the sun and widest on the part nearest the edge. Hence Wilson assumed that the great and stupendous body of the sun is made up of two kinds of matter, very different in their qualities, that by far their greater part is solid and dark, and that this immense and dark globe is encompassed by a thin covering of that resplendent substance from which the sun would seem to derive the whole of his vivifying heat and energy. Wilson went on to explain that the excavation of spots might be occasioned by the working of some sort of elastic vapor which is generated within the dark globe, and that the luminous material, which was more or less fluid, was acted upon by and tended to throw down and cover the nucleus. Sir William Herschel devoted considerable attention to the sun, and observing the variation in the sunspots, reached the conclusion in 1801 that it indicated a certain variability in the total amount of solar radiation, which he assumed might have some connection with terrestrial phenomena, especially the weather. He endeavored first in 1801 to trace connection between the price of wheat, naturally influenced by the effect of weather on the crops, and the occurrence of sunspots, claiming that when the latter were scarce there was a diminished solar activity, which caused colder weather, with obvious results. Ingenious as this theory was, there were not sufficient substantiating meteorological data. It finds, however, a counterpart in modern studies of the sun's heat, not necessarily connected exclusively with sunspots, however, whereby it is hoped to establish some useful knowledge of the relation between the amount of heat radiated from the sun and weather conditions on our earth. Herschel's observations of the sun and sunspots were continued by his son, Sir John Herschel, at the Cape of Good Hope, 1836 to 1837. John Herschel assumed that their motion was due to fluid circulations similar to those producing the trade and anti-trade winds on the earth. The spots, in this view of the subject, he said, would come to be assimilated to those regions on Earth's surface where for the moment hurricanes and tornadoes prevail, the upper stratum being temporarily carried downward, displacing by its impetus the two strata of luminous matter beneath, the upper, of course, to a greater extent than the lower, and thus wholly or partially denuding the opaque surface of the sun below. Such observation of sunspots, made with considerable thoroughness by the astronomers mentioned, as well as numerous others, did not establish any regularity in their appearance or effacement. It remained for Heinrich Schwab, 1790 to 1875, at Dessau, to announce in 1843 that the sunspot phenomenon reached a maximum probability in a decennial period. This announcement, although coming as it did after a patient study of the sun, attracted no particular attention until a series of sunspot statistics were published in Humboldt's Cosmos. Then the correctness of Schwab's observations and deductions was apparent to all. When compared by Dr. John Lamont and Sir Edward Sabine with various periodical magnetic disturbances, it was found that the two cycles of changes agreed with extraordinary exactness. It was a remarkable coincidence that the observations of a number of investigators were in complete harmony. A study of sunspot records established the decennial period more correctly at 11.11 years. Thus commenced a recognition that magnetic disturbances on the earth were related in some way to sunspot phenomena. For many years, no direct connection could be established, although various theories were forthcoming. Likewise, further attempts were made to identify the variations of sunspots with meteorological phenomena, but without success, until Wolf in 1859, by an examination of the Zurich Chronicles, 1000 to 1800 A.D., found data which established occurrences of the aurora borealis to be correlated with a disturbed condition of the sun. From this time on, the influence of the sun on terrestrial conditions assumed new importance. The beautiful phenomenon of the aurora, which consists of a glow in the sky about the north and south poles, had been observed for ages, but the first scientific connection of importance recorded was in 1716, when Halley stated that the northern lights were due to magnetic effluvia. In 1741, Hiorter at Uppsala observed that they produced an agitation of the magnetic needle. This connection was further demonstrated by Arago, 1819, so that by the middle of the 19th century the connection of the aurora with the sun, and in turn with terrestrial magnetism, was as evident as it was insufficiently explained. The first result of modern study of the sunspots was to put an end to the old notion that there was a dark and cold interior of the sun, and that the sunspots were merely rents in the brilliant cloud covering through which the interior portion could be seen. The late Professor S.P. Langley, one of the most active of the modern students of the Sun and its surface, thought that the filaments, which taken together constitute the penumbra, were everywhere present on the surface. Professor Hale states, he regarded them as resembling the stalks of a wheat field seen on end in the undisturbed photosphere, and revealing more of their true characteristics in the penumbra, where they are bent over and drawn out toward the central part of the spot. Langley believed that we are observing clouds of luminous vapors rising from the Sun's interior, the seats of convection currents which bring to the surface the immense supplies of heat radiated by the Sun into space. Separating these luminous columns are darker regions, characterized by a lower degree of radiation. The minute details can be recorded only with the greatest difficulty. Under ordinary atmospheric conditions, the solar image is not seen as a sharp and well-defined object, but its details are continually blurred by the effect of irregularly heated currents in our atmosphere. Even under the best conditions, the moments of very sharp definition are few, and the greatest patience and perseverance are required on the part of an observer who would record his impressions of the solar structure. At the best, drawings based upon visual observations must be unsatisfactory, since even the skilled hands of Langley could not secure the perfect precision which is so desirable. It accordingly might be hoped that here, as in other departments of solar research, photography would afford the necessary means of securing results unattainable by the eye. Unfortunately, however, this hope has only been partially realized. The influence of sunspots is not confined to magnetic and electrical phenomena. The researches of Koppen, which have been confirmed by Newcomb, show that the average temperature of the Earth, determined by the combination of a great number of thermometric observations made at several stations, indicated a fluctuation of 0.3 degrees to 0.7 degrees Celsius during the 11-year sunspot period. In other words, the temperature of the Earth's atmosphere indicates small fluctuations which correspond with the sunspot period, thus indicating that the solar heat radiation varies with the number of the sunspots. The mean temperature of the Earth is greatest at the time of minimum sunspots and lowest at the time of maximum sunspots. Hence the determination of the amount of heat radiated by the Sun at various times, especially at sunspot maxima and minima, is a matter of considerable terrestrial importance. The study of the sunspots, carried on by Professor Hale with the spectroheliograph and other apparatus, including special red-sensitive plates of considerable speed, reached an interesting stage in 1908 when it was demonstrated that sunspots are centers of attraction which draw toward them the hydrogen of the solar atmosphere. Subsequently, it was found that these spots are the seats of great cyclones, in which cool hydrogen gas is set whirling and is sucked down in the great maelstrom of the Sun, rushing into the center of the spot at a rate of about 60 miles a second. Consequently, the spots are the center of great solar disturbances which are of an electromagnetic nature. According to the modern electronic theory of matter and electricity, electrons, or minute particles of matter, in their terrific cyclonic velocity, produce magnetic lines of force. It was found by Professor Zeeman that when light is passed through a strong magnetic field, the lines of the spectrum are subdivided and appear double. This Zeeman effect Professor Hale has found in the spectrum of the sunspots. If one looks at the center of a spot, the light travels in the direction of the axis of the whirl or cyclone, while in viewing a spot at the edge of the Sun, the direction is at right angles to the axis and is manifested accordingly in the spectrum. This theory has been thoroughly confirmed, so that today it is known that sunspots are magnetic fields of great intensity. The important discoveries made by Professor Hale and his associates may thus be summarized as follows. First, that the spots are cooler than the surrounding region. Second, that they are centers of violent cyclones. And third, that they are magnetic fields of great intensity. In addition to the sunspots, the photosphere includes other interesting features, notable among which are the faculae, little torches, so named by Father Scheiner. These bright globular objects, besides the sunspots, are the only other phenomena of the Sun's surface visible by direct observation. Schroeder showed that the faculae are heaped-up ridges of the disturbed photospheric matter. Secchi and Young assumed that the faculae are the result of violent eruptive action of the sunspots, but it remained for the spectroheliograph to give a clear idea of their nature. Professor Hale states that they are usually most numerous in the vicinity of sunspots and near the Sun's limb they are sometimes very conspicuous, brilliant objects covering large areas. Near the center of the sun, however, they are practically invisible, though faint traces of them can sometimes be made out on photographs taken with suitable exposure. This increase of brightness toward the sun's limb is assumed to be due to the elevation of the faculae above the photospheric level and their escape from a considerable part of that absorption which so materially reduces the brightness of the photosphere. Rising above the denser part of the absorbing veil and thus suffering but little diminution of light, they appear near the sun's limb as bright objects on a less luminous background. The chief difference of the faculae from the rest of the photosphere lies in their greater altitude, as photographs have shown that they may be resolved into granular elements similar to those constituting the photosphere. But they are the regions from which immense masses of vapors rise to the solar surface, and for that reason are important in the solar mechanism. Near the edge of the sun, their summits lie above the lower and denser part of that absorbing atmosphere which so greatly reduces the sun's light near the limb, and in this region the faculae may be seen visually. At times they may be traced to considerable distances from the limb, but as a rule they are inconspicuous or wholly invisible toward the central part of the solar disk. The Kenwood experiments had shown that the calcium vapor coincides closely in form and position with the faculae, and hence the calcium clouds were long spoken of under this name. In the new work at the Yerkes Observatory, the differences between the calcium clouds and the underlying faculae became so marked that a distinctive name for the vaporous clouds appeared necessary. They were therefore designated flocculi, a name chosen without reference to their particular nature, but suggested by the flocculent appearance of the photographs. With the spectroheliograph, Professor Hale relates, it was at once found possible to record the forms, not only of the brilliant clouds of calcium vapor associated with the faculae and occurring in the vicinity of the sunspots, but also of a reticulated structure extending over the entire surface of the sun. From a systematic study of spectroheliograph negatives, in the course of which the heliographic latitude and longitude of the calcium clouds, or flocculi, in many parts of the sun's disk were measured from day to day by Fox, a new determination of the rate of the solar rotation in various latitudes has been made. This shows that the calcium flocculi, like the sunspots, complete a rotation in much shorter time at the solar equator than at points nearer the poles. In other words, the sun does not rotate as a solid body would do, but rather like a ball of vapor, subject to laws which are not yet understood. End of section 12.
Section 13 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy, Chapter 10, The Sun, 2, The Reversing Layer, the Chromosphere and Corona, Radiation Pressure and Solar Energy, Part 1. The so-called reversing layer was discovered by the late Professor Charles A. Young during the eclipse of December 22, 1870, on which occasion he placed the spectroscope with its slit tangential to the sun's limb so that it ran along a shallow bed of incandescent vapors. When the moon reduced the size of the crescent of the sun, the dark lines of the spectrum and the spectrum itself gradually faded away until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was covered by bright lines, more numerous than one could count. This phenomenon lasted about 2 seconds and gave the impression of a distinct reversal of the Fraunhofer spectrum, showing bright lines for dark in every case. That such a reversing layer should exist was demanded by Kirchhoff's theory of the production of the Fraunhofer lines and implied a stratum of mixed vapors at a lower temperature than that of the surface of the sun. It was by such a stratum that the missing rays of the solar spectrum were stopped. The spectrum from this portion alone could supply bright lines if the overpowering brilliancy of the solar background could be cut off, which can occur only at the time of an eclipse. This observation of Professor Young's, with its important bearing on the theory of Kirchhoff, was not confirmed until 1896, when photographic evidence was forthcoming. During the eclipses of 1898 and 1900, abundant corroborative material was obtained, and the reversing layer as a reality was conclusively demonstrated. The total depth of this reversing layer has been placed at from 500 to 600 miles. It continues in a normal state of tranquility, for little change is produced in the aspect of the dark lines. The chromosphere, or envelope of glowing gases, which covers the sun completely, was detected by observers of eclipses in the 18th and 19th centuries. There is a record in a letter from Captain Stannyan to Flamsteed, the British Astronomer Royal, describing an eclipse witnessed at Bern on May 1st, Old Style 1706, in which he states that the sun's, quote, getting out of the eclipse was preceded by a blood-red streak of light from its left limb, unquote. Halley and de Louisville in 1715 noted a similar phenomena, and it was also observed during annular eclipses of 1737 and 1748, but with the ruby brilliancy toned down to brown or dusky red by the surviving sunlight. During the eclipses of 1820, 1836, and 1838, similar observations were made, but it was not until the eclipse of the 8th of July, 1842, that the virtual discovery of the chromosphere as a solar appendage may be said to have been made. The eclipse of 1868, which was observed spectroscopically and photographically, as well as with the telescope, served to make clear the nature of the chromosphere and to reveal that it is a continuous envelope of hydrogen and other incandescent gases, some thousands of miles in thickness, and of the same eruptive nature as the prominences which are shot out from it. In other words, it seems to be a collection of minute flames set close together and giving it the appearance of a large conflagration. The summits of the flames of fire, which incline when the sun's activity is greatest, are erect during its phase of tranquility. The chromosphere is marked by an irregular distribution over the sun's surface, which in no way partakes of the character of an atmosphere. Professor Hale, in 1897, discovered a low stratum of carbon vapor. Such rare metals as gallium and scandium have been discovered with the spectroscope. The vapors of magnesium, iron, and several other substances are conspicuously represented in the spectrum of the chromosphere, and with the Yerkes telescope, the fine bright lines due to the vapor of carbon also may be seen. The solar prominences are conspicuous, eruptive, or flame-like emanations from the chromosphere which are seen at total eclipses of the sun. They project like red flames beyond the dark edge of the moon, and were first described by Lector Vesenius, a Swedish professor of Gothenburg, who observed the total eclipse of May 2nd, Old Style, 1733. One of these reddish clouds outside of the solar disk was so large that it could be detected with the naked eye. The phenomenon excited his admiration and wonder. The prominences were also observed in 1778 by the Spanish Admiral Don Antonio Ulloa, who was convinced of their connection with the sun on account of their color and magnitude. By some observers, the solar prominences were regarded as the illuminated summits of lunar mountains, and by Arago, they were described as solar clouds shining by reflected light. Abbe Pétal in 1842 spoke of them as self-luminous and as a third or outer solar envelope composed of the glowing substance of the bright rose tint, which produced mountains, just as clouds were piled above the Earth's surface. In 1851, Hind, an English astronomer, noted on the south limb of the moon, quote, a long range of rose-colored flames, unquote, which Dawes spoke of as a low ridge of red prominences, resembling in outline the tops of a very irregular range of hills. Airy also noted this rugged line of projections and spoke of its brilliancy and nearly scarlet color. But the truly solar origin of the phenomena was not conclusively demonstrated until 1860, when the prominences were photographed by Secchi and Delarue and shown to be independent of the motion of the moon. In 1868, with the growth of spectroscopy and solar chemistry, the gaseous nature of the prominences and their connection with the sun was made evident. They were found to consist of immense masses of hydrogen and helium gas rising from the chromosphere and reaching an altitude of hundreds of thousands of miles. The corona. The corona is a beautiful, lustrous solar wrapping which can be observed only during a total eclipse. The winged circle, the winged disk, or the ring with wings, as it is variously called, found upon Assyrian and Egyptian monuments, may be reproductions of the phenomenon. The first definite mention of a solar corona is to be found in Plutarch in connection with the eclipse which probably took place in 71 A.D. He writes that the obscuration caused by the moon, quote, has no time to last and no extensiveness, but some light shows itself around the sun's circumference, which does not allow the darkness to become deep and complete, unquote. Kepler mentions a ray of light seen around the eclipsed sun in 1567 and ascribes it to some sort of luminous atmosphere around the sun. In 1706, Cassini, observing an eclipse of the sun in France, saw the, quote, crown of pale light, unquote, around the lunar disk, and stated that it was caused by the illumination of the zodiacal light. Halley, observing an eclipse in London in 1715, describes minutely the phenomena of the luminous ring rising around the moon to a great height and showing considerable brilliancy. The eclipse of 1842 was the first to indicate the corona's great importance to astronomers, and from that date it received careful attention and earnest study. In 1869, Professor Harkness and Professor Young discovered a bright line of unknown origin in the coronal spectrum, showing that it consists in large part of glowing gases. With the advent of astronomical photography and with the development of the spectroscope, more attention than ever was given to the careful study of the corona in the limited time available on the occasion of a total eclipse. The corona is described by Professor Hale as a, quote, faintly luminous veil of light extending outward in long streamers from the surface of the photosphere to distances of several millions of miles and exceeded in brilliancy even in its brightest parts by the full moon. In many ways, its streamers resemble those of the aurora borealis, and it is indeed possible that their origin may be ascribed to some similar electrical cause. During the few minutes of a total eclipse, they are not seen to undergo change of form, but the outline of the corona does vary greatly from year to year in sympathy with the general variation of the solar activity. Spectroscopic observations have shown that the corona consists mainly of gases unknown to the chemist. That is to say, the lines in its spectrum do not coincide in position with the lines of any terrestrial element. Whether these gases, which are probably very light, will ultimately be found on the Earth cannot be predicted. Like helium, first known in the Sun, they may eventually be encountered in minute quantities in some mineral, where they have hitherto escaped the chemist's analysis. The fact that the lower part of the corona gives a continuous spectrum, with a feebler solar spectrum superposed upon it, indicates that minute incandescent particles are present, which are hot enough to radiate white light and which scatter enough sunlight to account for the presence of the solar spectrum, unquote. The strange line in the green portion of the spectrum does not correspond with that of any element with which we are acquainted upon the Earth, and accordingly a hypothetical element has been assumed to which the name coronium has been applied. Chemical composition. Anaximenes' idea that the sun was a glowing ball of incandescent iron came almost as near the truth as subsequent speculations by philosophers and astronomers until about the middle of the 19th century. In 1859, Kirchhoff's great discovery of the explanation of the Fraunhofer lines in the solar spectrum made it possible to ascertain the chemical composition of the sun. Thus, as has been shown, the bright-colored band formed of light from a small hole in Newton's shutter passing through a prism made that prism the forerunner of an instrument able to teach the nature and constitution of bodies far distant in the heavens. Thomas Melville had examined with a prism various flames in which different substances had been introduced, and had reached the conclusion by the middle of the 18th century that certain vapors, notably sodium, contained light which had a definite place in the spectrum. Melville's deep yellow ray became the sodium line in the spectroscope of Fraunhofer. When Kirchhoff noted the identity of certain lines characteristic of terrestrial elements and then assumed their presence in the Sun, he laid the foundation of the modern science of solar chemistry. Wherever light can be observed from a heavenly body, it is now possible to resolve it into its spectral elements and thus to identify the substances. In fact, as substances such as helium were found in the Sun by Lockyer, which had no terrestrial counterpart, hypothetical elements were assumed. The spectroscope has shown in the Sun the presence not only of gases such as hydrogen and helium, but iron, sodium, magnesium, calcium, and many other substances. Hence, the chemical composition of the Earth and the Sun are much the same, although there is evidence of the existence in the Sun of substances not yet found in the Earth. When the spectroscope was applied to the analysis of the chromosphere and its prominences, it was found that they are composed of the vapor of calcium and of the light gases helium and hydrogen. Sunspots, too, have been found to have a characteristic chemical composition, while the corona emits rays which probably indicate the presence in it of very light and tenuous gases. With the light given off by the Sun, there is to be considered a phenomenon which only recently has been demonstrated by experiment, namely that light exerts a pressure which can act on minute particles quite as effectively as gravitation. Gravitation, however, attracts entire masses, but pressure acts only on surfaces, so that a force, such as the pressure of light, to be effective must deal with very minute masses. If you subdivide a mass into a large number of minute particles, the effect of gravitation is not changed, but a point will be reached in the subdivision where particles may be obtained having much surface and very little weight. If such a particle has a diameter of 1/100,000th of an inch, it will be exactly balanced in space, pulled by gravitation, weight on the one hand, pushed by light on the other. If the particle is even smaller than 1/100,000th of an inch in diameter, the pressure of light upon it pushes it away with terrific force. It is the radiation of the Sun acting on the minute particles that produces the phenomenon of comets' tails, and it is this pressure which may be responsible for the brilliant phenomena of the corona, visible only during the vanishing moments of a total eclipse. No one has ever satisfactorily explained how the highly attenuated matter composing both the prominences and the corona is supported without falling back into the Sun under the pull of solar gravitation. Now that Arrhenius has cosmically applied the effects of light pressure, a solution is presented. How difficult it is to account for such delicate streamers as the prominences on the Sun is better comprehended when we fully understand how relentlessly powerful is the grip of solar gravitation. The Sun admittedly projects vapors into space, vapors which must condense into drops when they encounter the cold of outer space. If the drops are larger than the critical size which determines whether light pressure or gravitation shall prevail, they will be snatched back by the Sun's gravitational attraction and give rise to the curved prominences that are often observed. If they have approximately the critical diameter, they will float above the Sun in the form of beautiful carmine clouds, balanced in space by the equal and oppositely acting forces of gravitation and radiation pressure. These clouds have hitherto been particularly puzzling, for in the absence of a dense solar atmosphere, their existence seemed a celestial paradox. If the condensed drops are smaller than the critical diameter, they will be projected by the pressure of light far beyond the Sun to form the beautiful pearly corona. From the fact that comets have passed through the corona without any very apparent retardation, some idea of its tenuity can be gained. Assuming that the corona consists of particles of such size that the radiation pressure on each exactly equals its weight, Arrhenius finds that the entire corona weighs no more than 12 million long tons, which is equivalent to 400 large transatlantic steamers and is not more than the amount of coal burned on the Earth every week. Compared with the infinity of the space in which it is poised, the Earth is smaller than a vanishingly small speck on a sheet of paper having an area of many square miles. So far as the Earth is concerned, the Sun is very much in the position of a man who throws away all but a single cent of a fortune consisting of $23 million for only 1/2,300,000,000th of his radiated energy reaches this globe. What then becomes of the huge number of corpuscles which are shot from the Sun and which never strike the Earth? It is conceived by Arrhenius and his followers that many of them must collide with corpuscles discharged by suns other than that of this solar system, suns ineffably distant, so that their light reaches the Earth only after the lapse of countless centuries, and so that they are seen not as they gleam now, but as they gleamed when Egypt was young, and Greece was a wilderness inhabited by savages. Such collisions must result in the formation of large masses up to a limit determined by the electrical charges carried by the corpuscles. End of section 13.
Section 14 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 10, Solar Energy, Part 2. Solar energy. The Earth depends upon the Sun for its supply of heat and light. The Sun is transmitting heat to the Earth, and unless the supply of energy is being replenished in some way, it is obvious that it must be losing in heat and temperature. From its effect on the Earth, an estimate can be had of the amount of heat radiated by the Sun annually. If it be assumed that the Sun has the same heat capacity as water, and hydrogen is the only substance with a greater heat capacity, it would fall in temperature about 4 degrees Fahrenheit annually. If, therefore, the great luminary were simply a hot body cooling off, its present rate of radiation could not be maintained for more than 3,000 years. That the Sun has been radiating a much longer period than this is obvious from geological and biological evidence, so that some other cause must be sought. Up to the 19th century, the doctrine of infinite durability was generally held by astronomers and geologists. For that reason, no particular attention was paid to the nature of the heat of the Sun and its source, but with the formulation of the doctrine of the conservation of energy, it was realized that the energy of the Earth must proceed from the Sun for the greater part, and consequently it became necessary in turn to question the source of solar heat. Robert Mayer, to whom is due the earliest conception of the conservation of energy, asked himself, "If the Sun is hot, why does it not cool off?" In 1848, Mayer published some answers to his own question in a paper which failed to receive the approval of the French Academy of Sciences. His conclusions were as follows. The Sun cannot be a glowing mass sending out radiation without compensation. Solar heat cannot be due entirely to chemical changes, nor can it be due to solar rotation. In his opinion, it was the result of meteors falling into the Sun. He did not overlook the fact that the resulting increase in the mass of the Sun would increase its attraction for the planets and would shorten the sidereal year. This was contrary to the facts of observation, and Mayer was forced to an incorrect conception of the undulatory theory of light to explain the situation. 6 years later, William Thomson, subsequently Lord Kelvin, reached independently almost the same conclusion as Mayer, but he was able to explain the increase in the Sun's mass resulting from meteoric showers. For according to the gravitation theory, the added matter is drawn from space, where it acts on the planets with very nearly the same force as when incorporated in the Sun. Lord Kelvin then ventured an estimate of the age of the Sun, which was the first attempt in this direction made by a physicist. He assumed that the solar energy of rotation was derived from the fallen meteors, which, allowing for the constant loss of solar energy by radiation, could be acquired in 32,000 years. Taking into consideration the limited amount of meteoric matter available near the Sun, he concluded that sunlight cannot last as at present for 300,000 years. This theory attracted little attention when promulgated by him in 1854, and was abandoned by him later. But in the same year, Helmholtz, working along the lines of the nebular hypothesis of Kant and Laplace, derived the heat of the Sun from the contraction of the nebula from which the Sun and planets were formed. He asserted also a further contraction of the Sun, now assumed to be in progress, by which the kinetic energy obtained was converted into heat and compensated for the loss of solar heat by radiation. Accordingly, if the Sun contracts 1/10,000th part of its radius each year, enough heat would be generated to supply radiation for 2,100 years. Helmholtz's computation gives 22 million years as the probable age of the Sun, based on a uniform radiation and homogeneous density of that body. Later, S. P. Langley, with experimental data derived from the direct radiation of the Sun, reduced this age to 18 million years. This theory immediately supplanted that of the falling meteors, which more serious reflection demonstrated could account only for the slight increase in the solar heat as compared with the energy of shrinkage. Lord Kelvin in 1862 returned to the subject, favoring a theory like that of Helmholtz's, concluding that we may accept as the lowest estimate for the Sun's initial heat 10 million times a year's supply at the present rate, but 50 million or 100 million as possible in consequence of the Sun's greater density in his central parts. As for the future, inhabitants of the earth cannot continue to enjoy the light and heat essential to their life for many million years longer, unless sources now unknown to us are prepared in the great storehouse of creation. Studies of the Sun's heat were continued by Lord Kelvin, and in his theory he incorporated a discovery made in 1870 by J. Homer Lane, an American, which paradoxically demonstrated that within certain limits, the more heat a gaseous body loses by radiation, the hotter it will become. This theory of Helmholtz's, as modified by Kelvin, encountered a serious rival in 1882, when Sir William Siemens proposed that a rotating sun hurled by centrifugal action at the equator enormous quantities of gas into space, which returned to it again at the poles, somewhat after the manner of a regenerative furnace. Helmholtz's theory was modified in 1899 by Professor T.J.J.C., who abandoned the German scientist's hypothesis of homogeneous density for the Sun and applied Lane's law, investigating minutely the more complex case of central condensation. As the result of his study, the probable age of the Sun was extended from 22 million to about 32 million years. All of these researches came before the discovery of radium, and when the extraordinary properties of this new substance were known, it was stated that a bare fraction of a % of radium present in the Sun would account for and make good the heat that is annually lost by radiation. Should this hypothesis hold good, an entirely new aspect is given to the problem of solar heat and to the heat of the Earth. This innovation, advanced by members of the younger school of physicists, all of whom had prosecuted with vigor researches in radioactivity, did not appeal to Lord Kelvin, who maintained in 1906 that the gravitation theory was still sufficient to account for the Sun's heat. No evidence has been produced of the presence of radium in the Sun, although helium has been found there. As helium is obtained from radium, the existence of radium in the Sun is quite probable. Sir George H. Darwin, in discussing the effect of these recent discoveries on solar age, says, "Knowing as we now do that an atom of matter is capable of containing an enormous store of energy in itself, I think we have no right to assume that the Sun is incapable of liberating atomic energy to a degree at least comparable with that which it would do if made of radium. Accordingly, I see no reason for doubting the possibility of augmenting the estimate of solar heat, as derived from the theory of gravitation, by some such factor as 10 or 20. It is obvious, therefore, that while the contraction theory explains the origin of a vast amount of the Sun's heat, yet there are other sources of internal energy which recent discoveries plainly indicate are of great importance, so that the scientist at this stage is unable to declare positively the age of the Sun or to make any accurate estimate as to the probable duration of the time through which it will afford light and heat to the Earth and the other planets. Nevertheless, it seems assured that millions of years hence, how many cannot even roughly be determined, the sun will be reduced from a ball of glowing vapor to a gigantic black cinder rushing through space. Unwarmed by any central luminary, its crust will be washed by oceans of air liquefied by a cold too intense for any living creature to endure. The light of the sun is obviously more intense than any other luminant known to man. If compared with the full moon, 600,000 times as much light is received from the sun. Expressed in another way, the sun gives over 60,000 times as much illumination as a standard candle at a distance of 1 yard. But not all of the light and heat which is radiated from the sun comes to the earth. Professor Langley, in his experiments at Mount Whitney in 1881, found that a clear atmosphere would cut off 40% of the rays coming perpendicularly to the Earth's surface. Gases in the atmosphere, such as carbon dioxide, cut off even a greater amount, and the general absorption is greater at the violet end than at the red. It is for this reason that high altitudes and a clear atmosphere are essential for solar investigation. And for this reason, too, that the setting sun appears red, the bluish rays being absorbed in traversing a greater amount of terrestrial atmosphere than when the sun is high in the sky. The temperature of the sun can be estimated from its brilliancy and from spectroscopic and bolometric studies. It is a common experience that a filament of an incandescent lamp emits more light and glows more brightly when the amount of current is increased. At first the filament is red, but as more current is permitted to flow it becomes yellow and finally a brilliant white. This is marked by an increase in temperature, and secondly, the temperature depends upon the brilliancy of the glow. The same analogy holds good in the case of the sun and the stars. If the wavelength of the radiation is known, and the color which emits the greatest amount of heat in the spectrum, and this can be measured by the bolometer by a simple law, it is possible to calculate the absolute temperature of a star. Then, by deducting 270 degrees from the result, its temperature in the ordinary centigrade degrees is obtained. Thus, in the case of the sun, the maximum heat radiation occurs in the greenish-yellow light, which gives a temperature for the rotating disk of the sun of about 5,000 degrees centigrade or 9,000 degrees Fahrenheit. The atmospheric absorption already referred to serves to cut down the intensity of the radiation, so that, taking this and other amounts into consideration, the temperature of the sun's disk can be estimated at about 6,200 degrees centigrade. Similar investigation in the case of Sirius and Vega, which are white or younger stars, give a temperature about 1,000 degrees Celsius higher than that of the sun, while the red star Betelgeuse, which is a declining star, older than the sun, has a temperature some 2,500 degrees centigrade less. The temperature of the sun furnishes different results, depending on the manner in which the problem is attacked. Arrhenius, in his work on Worlds in the Making, summarizes recent work and states that, from the intensity of the radiation, Christensen and afterward Warburg calculated a temperature of about 6,000 degrees centigrade. Wilson and Gray found for the center of the sun 6,200 degrees, which they afterward corrected into 8,000 degrees. Owing to the absorption of light by the terrestrial and the solar atmospheres, two low values are always found. That applies to a still greater extent to any estimate based upon the determination of that wavelength for which the heat emission from the solar spectrum is maximum. Le Chatelier compared the intensity of sunlight filtered through red glass with the intensities of light from several terrestrial sources of fairly well-known temperatures treated in the same way. These estimates yielded to him a solar temperature of 7,600 degrees centigrade. Most scientists accept an absolute temperature of 6,500 degrees, corresponding with about 6,200 degrees centigrade. That is what is known as the effective temperature of the sun. If the solar rays were not partially absorbed, this temperature would correspond with that of the clouds of the photosphere. Since red light is little absorbed, comparatively, Le Chatelier's value of 7,600 degrees centigrade and the almost equal value of Wilson and Gray of 8,000 degrees centigrade should represent approximately the average temperature of the outer portions of the clouds of the photosphere. The higher temperature of the faculae is evident from their greater light intensity, which, however, may be partly due to their greater height. Carrington and Hodgson saw, on September 1, 1859, two faculae break out from the edge of a sunspot. Their splendor was 5 or 6 times greater than that of the surrounding parts of the photosphere. That would correspond with a temperature of about 10,000 or 12,000 degrees centigrade. The deeper parts of the sun which broke out on these occasions evidently have a higher temperature, and this is not unnatural, since the sun is losing heat by radiation from its outer portions. At all events, the Earth receives a large amount of energy in the form of light and heat, which amounts to 3 horsepower for every square yard of space perpendicular to the sun's rays. And while this really is not readily available for mechanical purposes, yet solar engines have been constructed in which this energy has been transformed into power. While the energy of the sun is not, generally speaking, available for mechanical purposes, yet indirectly the heat received by the Earth has made possible plant and animal life, on which depends the source of all energy. The transmission of the sun's heat to the Earth is one of the important problems of present-day physics and meteorology, inasmuch as the amount of radiation or heat emitted by the sun, spoken of by physics as the solar constant, and the relation of this radiation to terrestrial temperature, as well as the study of the radiation of different parts of the sun's disks, are all topics of fundamental importance. The solar constant is measured outside of the Earth's atmosphere at mean solar distance, and the intensity of radiation is employed for a unit which, when fully absorbed for 1 minute over a square centimeter of area placed at right angles to the ray, would produce sufficient heat to raise the temperature of a gram of water 1 degree centigrade. If once the original quantity and kind of heat emitted by the sun be known, its effect on the constituents of the atmosphere on its journey to the Earth, how much of it reaches the soil, how through the change of the atmosphere it maintains the surface temperature of our globe, and finally, how in diminished quantity, or altered kind, it is returned to outer space, it would be possible to predict nearly all of the phenomena of the weather. Thus, it has been known that when there is a small decrease in the solar radiation, there follows a marked and general decline in temperature. So that, knowing the variation of radiation, it should be possible to predict changes in climate. These data are secured by measuring the total intensity of the radiation as it arrives at the Earth's surface with the pyrheliometer, or thermometer with blackened bulb, carefully protected from all other influences except the direct rays of the sun. And in the second place, by measuring the heat or energy in different parts of the solar spectrum with the spectrobolometer. The absorption of the atmosphere nearer the Earth for different areas requires measurements to be made at several stations. For at Washington, near the sea level, the intensity of radiation actually observed is only about 3/4 as great as that observed in the clear atmosphere of Mount Wilson at a height of 6,000 feet. Recent observations made at Mount Wilson and Washington by Mr. Abbott of the Astrophysical Laboratory of the Smithsonian Institution indicate that heat sent out to the Earth from the sun in the course of a year is capable of melting an ice shell 114 feet thick over the whole surface of the Earth. The solar radiation is not a constant quantity, but varies with the decrease in solar distance, the changes occurring from month to month and from year to year. The variation is due to the changes in the source of radiation rather than to the effects of our atmosphere or external causes. The distance and position of the sun as regards the other members of the solar system has been considered in a previous chapter. It is known that its apparent diameter is 32 arc minutes, 4 arc seconds, which corresponds with 866,500 miles, or 109.5 times the diameter of the Earth. This would give it an area 11,950 times that of the Earth and a volume 1,306,500 times greater. The actual mass of the Sun is 332,000 times that of the Earth, but its average density is only about a quarter as great, so that the Sun, which has a density of 1.41 as compared with water, is 4 times as large as it would have to be if its density were the same as that of the Earth. Taking into consideration this lightness as well as the high temperatures prevailing in the Sun, one is forced to the conclusion that the body of the Sun must be in a gaseous state. The conditions under which the gases are found must be quite different from those with which we are acquainted on the Earth. Gravity at the surface of the Sun exceeds by more than 27 times gravity on the Earth. The motion of the sun as regards the other stars in the heavens has been treated elsewhere, but it is proper here to refer to its rotation on its axis from west to east, which takes place in a period of about 25 days and is apparent from the motion of the sunspots, though it can also be detected by directing a spectroscope toward the edges of the limb and noting by Doppler's principle how one side is approaching the observer and the other is retreating. The time of rotation is not the same for all parts of the disk, but depends upon the position of the spots selected. Those nearest the equator show the most rapid rotation. End of section 14.
Section 15 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Wolt Wheeler. Astronomy. Chapter 11, Mercury. Ancient records make no mention of the discovery of Mercury, yet the existence of the planet was surely known even in the days of Nineveh, when a chief astronomer directly refers to the planet in a report which he made to King Assurbanipal of Assyria. The planet is occasionally mentioned in early and medieval astronomical literature. It is stated that Copernicus regretted that he had never been able to observe it properly in the high altitude of Frauenburg. That the planet should have been overlooked by the ancients is not strange when it is considered that it is never visible in the higher altitudes except occasionally near the horizon, just after sunset or before sunrise. In the clear sky over an eastern desert, the primeval astronomer doubtless saw this bright star in that part of the horizon where the setting sun was still shedding its beams. Its luster diminishes as the planet draws near the horizon at sunset, until finally it sets so soon after the sun that it is invisible. Years may elapse before a similar opportunity is afforded. If a similar phenomenon took place at sunrise, the primitive astronomer might have inferred that Venus and Mercury were identical, especially as a long series of observations would establish the fact that one of these bodies was never seen until the other had disappeared. Accordingly, some of the ancient astronomers assumed that there was but one morning and evening star. But as records accumulated, it was recognized that there were two bodies which might serve as morning and evening stars. A certain regularity in the recurrence of each planet was noted, and it was possible to make predictions of accuracy as to the time when either could be seen after sunset or before sunrise. While by the time of Plato it was known that Venus and Mercury performed their revolutions in approximately the same time, it was recognized that Mercury's period was different and more rapid than that of other planets. An older tradition, attributed to the Egyptians, stated that both planets revolved around the sun. Ptolemy states that they could be regarded as oscillating to and fro on each side of the sun. That the ancient astronomers might well have been confused by the appearance of Mercury as morning and evening star follows from a consideration of the planet's position and motion relatively to the sun and the earth. The consideration, moreover, applies to Venus as well. Quoting C.G. Dolmage's Astronomy of Today, when furthest from us, Mercury is at the other side of the sun, and cannot then be seen owing to the blaze of light. As it continues its journey, it passes to the left of the sun, and is then sufficiently away from the glare to be plainly seen. It next draws in again toward the sun, and is once more lost to view in the blaze at that time of its passing nearest to us. Then it gradually comes out to view on the right hand, separates from the sun up to a certain distance as before, and again recedes beyond the sun, and is for the time being once more lost to view. To these various positions technical names are given. When the inferior planet is on the far side of the sun from us, it is said to be in superior conjunction. When it has drawn as far as it can to the left hand, and is then as east as possible of the sun, it is said to be at its greatest eastern elongation. Again, when it is passing nearest to us, it is said to be in inferior conjunction. And finally, when it has drawn as far as it can to the right hand, it is spoken of as being at its greatest western elongation. The continual variation in the distance of the inferior planets, Venus and Mercury, from the Earth during their revolution around the Sun, will of course be productive of great alterations in apparent size, which no doubt also had its effect in bewildering the ancients. At superior conjunction, being then farthest away, Mercury ought to show the smallest disk, while at inferior conjunction, being the nearest, it should appear much larger. When at greatest elongation, whether eastern or western, it should naturally present an appearance midway in size between the two. From these considerations, it would seem that the best time for studying the surface of Venus or Mercury is at inferior conjunction, or when the planet is nearest to the Earth. But that this is not the case will at once appear if it is considered that the sun's light is then falling upon the side most distant, leaving the proximate side unilluminated. In superior conjunction, on the other hand, the light falls upon the side of the planet facing the Earth. But the disk is then so small, and the view besides is so dazzled by the proximity of the sun, that observations are of little avail. In the elongations, however, the sunlight comes from the side, and so we see one half of the planet lit up, the right half at eastern elongation and the left half at western elongation. Piecing together the results given at these more favorable views, it is possible bit by bit to gather some small knowledge concerning the surface of Mercury or Venus. Consequently, it will be seen that the inferior planets show various phases comparable with the waxing and waning of the moon in its monthly round. Superior conjunction is, in fact, similar to full moon, and inferior conjunction to new moon, while the eastern and western elongations may be compared respectively with the moon's first and last quarters. When these phases were first seen by the early telescopic observers, the Copernican theory was felt to be immeasurably strengthened, for it had been pointed out that if this system were correct, the planets Venus and Mercury, were it possible to see them more distinctly, would of necessity present phases when viewed from the Earth. The apparent swing of an inferior planet from side to side of the sun, at one time on the east side, then passing into and lost in the sun's rays, to appear once more on the west side, is the explanation of what is meant when one speaks of an evening star or a morning star. Mercury of Venus is called an evening star when it is at its eastern elongation, that is to say, on the left hand of the sun. For being then on the eastern side, it will set after the sun sets, as both sink in their turn below the western horizon at the close of day. Similarly, when either planet is at its western elongation, that is to say, to the right hand of the sun, it will precede him, and so will rise above the eastern horizon before the sun, receiving therefore the designation of morning star. Mercury's motions were early studied. With the planet was associated the first of the remarkable astronomical predictions that now have become almost commonplace, so carefully are they worked out by astronomers. Kepler, from his studies of the motions of the planet, was the first to realize that if the orbit of Mercury, which, as has been seen, lies within that of the Earth, and thus nearer the sun, were exactly circular, and in the plane of the ecliptic, a transit of Mercury across the sun's disk would occur once in each synodical revolution, or period between two successive conjunctions of the planet with the sun as seen from the Earth. The epoch of the transit could be calculated very easily. But Mercury's orbit is inclined 7 degrees to the ecliptic, and is very eccentric, for which reason his calculations were only approximately correct. It was in 1627 that Kepler predicted transits of both Mercury and Venus across the Sun, and assigned the date of November 7th for the former. Gassendi, to whom was entrusted the task of proving Kepler's prophecy, began his observation on the 5th of November, watching the image of the Sun formed by a lens on a white screen from light emitted through a hole in a dark room. But Kepler was not in error by as much as that. Only 5 hours after the time assigned did the transit actually begin. Thus was commenced a series of observations of the time when Mercury crosses the great central luminary of this system. These transits are by no means rare, for 13 of them were observed in the 19th century. They afford opportunity for observation which enables the movements of the planet to be calculated with accuracy. After the transits of 1661 and 1677, Lahire constructed new tables of Mercury and predicted a transit on May 5, 1707. The calculation was in error by nearly a day. After the transit of May 1753 had been observed several hours later than Lahire's, and as much earlier than Halley's prediction, Lalande constructed new tables and predicted the transit of 1786, which actually took place 53 minutes later than the time announced by Lalande and about as much earlier than the time computed by Halley's tables. Lalande then corrected his tables and predicted the transits of 1789, 1799, and 1802 with a fair approach to accuracy. The tables compiled by Lindenau in 1813 still left much to be desired. The problem of Mercury's motion was in this condition when it was attacked by Leverrier, who was under no illusion in regard to its difficulty. Leverrier did not succeed in overcoming the difficulty until 1859. As a result of his work, supplemented by that of later investigators, astronomers are now in possession of at least fairly accurate information on the subject of the planet's orbital phenomena. It is known, for example, that Mercury is the swiftest in its movements of all the planets. With the exception of some of the satellites, it has an orbit that departs most from the circular form. In other words, an orbit marked not only by the greatest eccentricity, but also by the greatest inclination of all planetary orbits to the ecliptic. This eccentricity of the orbit is such that the Sun is 7.5 million miles out of its center, while the actual distance of the planet from the Sun ranges from about 29 million miles to 53 million, or a mean distance of about 36 million of miles. The velocity varies from 35 miles a second when the planet is at perihelion, or nearest the Sun, at the pointed end of its oval course, to about 33 miles a second at aphelion. To explain the perturbations in Mercury's motion, Abbe Moreau has recently advanced the following hypothesis. The Sun is unquestionably surrounded by matter, which gives rise to the observed phenomena of the corona. Photographs made during the eclipse of 1905 showed an outer corona extending to a hitherto unsuspected distance from the Sun. This outer corona is ellipsoidal, and its major axis is very nearly coincident with that of the zodiacal light. This region, then, is filled with a resisting medium, composed of matter which is gradually falling in toward the Sun. The mechanism of this fall, or contraction, is very complex, and as we have no idea of the identity of the matter, it is difficult to calculate its changes in form. The resistance which the medium opposes to a moving body is likewise difficult to estimate, but we know from the observed acceleration of comets that this resistance is by no means negligible. At the epochs of maximum coronal development, this resisting medium may easily extend to the orbit of Mercury. Hence, that planet, in its revolution around the Sun, must traverse masses of rarefied gas and swarms of minute particles by which its course is modified. We are far from knowing the quantitative effect of the resisting medium. and much study of the corona will be required to complete the solution of this interesting problem. Because of the lack of surface markings, the rotation periods are very uncertain. Recently, Professor Macquart in France has deduced a rotation of 24 hours, 8 minutes. G. Schiaparelli has put forward the view that both Venus and Mercury rotate in a time equal to the individual period of revolution around the Sun, and thus always turn the same face toward the Sun. Such a motion, which is analogous to that of the Moon around the Earth, could be easily explained as the result of tidal action at some past time when the planets were, to a great extent, fluid. This may be true, as Mercury is one of the planets which has no moon, and consequently will be influenced directly and solely by the Sun insofar as tidal phenomena are concerned. These tidal effects must be especially severe on account of the proximity of Mercury to the Sun. Because of this lack of a satellite, the mass of the planet is very difficult to determine. At various times, Laplace, Encke, and Leverrier have given values of 1/9 to 1/30 of the Earth's mass. The first convenient opportunity of placing this planet in a gravitational balance of determining its mass was presented in August 1835, when Encke's comet, in the course of its eccentric path through the solar system, penetrated within the orbit of Mercury at its perihelion. The attractive power of the planet produced only a slight deviation from the regular course of the comet, sufficient, however, to show that the value previously assumed for Mercury's mass was nearly twice too large. At the same time, the calculations made from these data have not removed the uncertainty that still prevails upon this point. Simon Newcomb decided on a value of about 1/21st of that of the Earth, while William Harkness made it 1/25th. Beyond its motion, comparatively little is known of Mercury. The spectroscope seems to indicate that the atmosphere of Mercury contains water vapor, just as does the Earth. But the studies of Professor Lowell at Flagstaff, Arizona, do not show any signs of clouds or obscurations, and there are no indications of any atmospheric envelope. In fact, the surface of Mercury has been termed colorless, a geography in black and white. The first student of the surface of Mercury was Johann Hieronymus Schröter, 1745 to 1816, who, as will be seen, was a pioneer in the study of the topography of the Moon. In April 1792, Schröter concluded from the gradual degradation of light on its brightly illuminated disk that Mercury possessed a tolerably dense atmosphere. During the transit of May 7, 1799, he was struck with the appearance of a ring of softened luminosity circling the planet to a height of 3 minutes and about a quarter of its own diameter. Referring to this ring as softened luminosity, Agnes Clerk writes in her History of Astronomy, "Although a mere thought in texture, it remained persistently visible both with the 7-foot and 13-foot reflectors, armed with powers up to 288. A similar appendage had been noticed by Desplantades of Montpellier, November 11, 1736, and again in 1786 and 1789 by Prosperin and Lagergus. But Herschel, on November 9, 1802, saw the preceding limb of the planet projected on the Sun cut the luminous solar clouds with the most perfect sharpness. The presence, however, of a halo was unmistakable in 1832, when Professor Moll of Utrecht described it as a nebulous ring of a darker tinge approaching to a violet color. Again, to Sir William Huggins and Stone on November 5, 1868, it showed as lucid and most distinct. No change in the color of the glasses used or the powers applied could get rid of it, and it lasted throughout the transit. It was next seen by Christie and Duncan at Greenwich, May 6, 1878, and with much precision of detail by Trouvelot at Cambridge, Massachusetts. Professor Holden, on the other hand, noted at Hastings-on-Hudson the total absence of all anomalous appearances, nor could any vestige of them be seen by Bernard at Lick on November 10, 1894. Various effects of irradiation and diffraction were, however, observed by Lowell and W. H. Pickering at Flagstaff, and Davidson was favored at San Francisco with a glimpse of the historic aureola, as well as of a central whitish spot which often accompanies it. That both are somehow of optical production can scarcely be doubted. The planet's physical condition presents many problems, and the spectroscope affords little information as to its constitution. As it shines only by reflected light from the sun, its spectrum is but a fine echo of the Fraunhofer lines. An atmosphere like that of the earth was suspected, however, by H. C. Vogel in 1871 from his spectroscopic studies, though on the very slightest grounds. Later observations made at the Potsdam Observatory by Miller confirm this conclusion and demonstrate that Mercury has a rough rind of dusky rock, which absorbs all but 17% of the direct light radiated upon it by the nearby sun. This would seem to show the utter absence of any appreciable Mercurian atmosphere. The probable lack of atmosphere is also shown by the circumstance that when Mercury is just about to transit the face of the sun, no ring of diffused light is seen to encircle its disk, as would be the case if it possessed an atmosphere. According to the Belgian astronomer Stroobant, the linear diameter of Mercury expressed as a fraction of the Earth's is 0.350, instead of the previously accepted 0.373. The radius 2,232 kilometers, 1,386.7 miles, and the volume compared with that of Earth is 0.042. End of section 15. Section 16 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy. Chapter 12, Part 1. For all time, Venus has been known as evening and morning star. By the ancients, it was supposed to be two separate bodies, which were named Phosphorus, Lucifer, or morning star, and Hesperus, Vesper, or evening star. For Pythagoras in the 6th century B.C. has claimed the honor of discovering the identity of the two stars, but it was probable that he restated the views of Eastern astronomers. As the most brilliant star in the heavens, Venus is certainly the one that has always been most observed. Glittering in the sky like a clear diamond, its pure white light, which on a night where there is no moon is strong enough to cast a shadow, naturally would impress all whose lives are spent out of doors. Hence Venus has always figured in literature as the shepherd's star. Homer speaks of the planet as Callistus, the beautiful, and as a type of beauty, its worship figures in all mythologies. At a time when the planets were personified as gods and goddesses, it is easy to understand why this star was selected to typify love. Not only on account of its splendor in the evening sky, but for other phenomena, Venus is familiar in history and literature. The historian Varro, 116-28 B.C., states that Aeneas, on his voyage from Troy to Italy, saw this planet constantly above the horizon, and the same historian is quoted by St. Augustine as speaking of a change in the color and brilliancy of Venus. In 1716, the visibility of Venus in full daylight was hailed as a marvel by the people of London, and in 1750 its appearance at noon aroused general astonishment in Paris. Again, in 1797, when Napoleon returned to Paris from his conquest of Italy, he found the attention of the populace divided between his reappearance and a similar striking midday phenomenon. In fact, Bonaparte always associated this star with his fortunes, and one evening, while engaged in viewing the starry heavens, pointing to the planet, said to Prince Talleyrand, "Do you see? That is my star. So long as it shines, I will have no doubt of success." In more recent times, many brilliant appearances of the planet have been observed, the interval between periods of greatest visibility amounting to 8 years. At one of these, in April 1905, at Cherbourg, Venus appeared as a bright meteor of appreciable size and full form, an effect which was due partly to the formation of a halo. According to the Ptolemaic theory, Venus was always between the Earth and the supposed orbit of the Sun. Hence it was possible that, at the most, but half of its illuminated surface could be visible to the Earth. When Galileo, with his telescope in 1610, made the striking discovery that Venus appeared in various phases, just as the Moon, exhibiting the gibbous as well as the crescent phase, it was a strong and almost the last argument necessary to establish beyond question the Copernican theory that the planets revolve around the Sun. Were Venus as large as Jupiter, for example, the phases would readily be discerned by the unaided eye. Indeed, Sir Robert Ball has wondered what would have been the effect on the history of astronomy had Venus been of the size of Jupiter, so that its crescent form could have been seen without a telescope. Then the elementary truth would have been apparent that Venus was a dark body revolving around the Sun. The analogy between it and our Earth would have been at once perceived, and the theory of Copernicus long since might have been established. The mean distance of Venus from the Sun is 67,200,000 miles. With the exception of the Moon and an occasional comet, no other heavenly body comes so near the Earth at any time. The orbit is marked by the smallest eccentricity in the planetary system, and is therefore more nearly circular than that of any other planet. The planet's greatest and least distance from the Sun vary from the mean only by about 470,000 miles each way. Venus is the nearest planet to the Earth, as there is only 26 million miles between the orbits of the two at inferior conjunction or their nearest approach. Yet Venus is not as well known as Mars, since when Venus passes nearest the Earth, it is then between it and the Sun, so that the hemisphere which is illuminated is not visible to the Earth. The appearance of Venus in the sky as the evening and the morning star was no less impressive to the ancients than the beautiful character of the star itself. It is as familiar now as it was to the shepherds of old that when Venus disengages himself in the evening from the rays of the setting sun, it departs from the Sun a little more every night, increasing its brilliancy until a certain distance in the east is reached, appearing, like the Moon, to travel toward the left of the observer. At the end of a few months it has removed itself from the Sun to an angular distance that may amount to as much as 48, at which time the planet sets more than 3 hours after the Sun. After shining for some months, little by little the planet begins to return toward the Sun, receding more and more from the Earth, then passing behind the central luminary, and thus ceasing to be the evening star. After an interval, a new star is seen in the early morning, to precede the rising of the Sun, advancing by imperceptible degrees every day, and eclipsing likewise all the bodies of the heavens by its dazzling light. At this time it proceeds toward the west, that is, toward the observer's right hand, and we have now the morning star. After having preceded the rising of the Sun by 3 hours, Venus resumes its course anew toward the Sun, and again is lost in the glare of day. It is then passing between the Sun and the Earth, and is at its greatest proximity to the Earth. Sometimes it passes just in front of the Sun, as it did in 1874 and 1882, which phenomenon is known as a transit. As it happens but twice in a century, a transit is an occurrence of considerable importance to astronomers. These transits are valuable for the easy determination of the position of the planet, for the investigation of its atmosphere, and for the determination of the solar parallax by comparing the amount of apparent displacement in the planet's path across the solar disk when the transit is observed at widely separated stations on the Earth's surface. These transits occur in June and December, taking place in cycles whose intervals are 8, 105.5, 8, 121.5 years. They have occurred on the following dates: December 7th, 1631, December 24th, 1639, June 5th, 1761, June 3rd, 1769, December 9th, 1874, December 6th, 1882, and will occur again on June 8th, 2004, and June 6th, 2012. The first observed transit, namely that of 1639, was watched in England by two persons, Jeremiah Horrocks and a friend William Crabtree, whom Horrocks had forewarned of its occurrence. That the transit was observed at all was due entirely to the remarkable ability of Horrocks. According to the calculations of Kepler, no transit could take place that year, 1639, as the planet would just pass clear of the lower edge of the sun. Horrocks, however, worked the question out for himself and came to the conclusion that the planet would actually traverse the lower portion of the sun's disk. The event proved him to be right. Horrocks, who was said to have been a veritable prodigy of astronomical skill, unfortunately died about 2 years after the celebrated transit in his 22nd year. The transits of Venus next observed in 1761 and 1769 were taken advantage of by Edmund Halley to suggest a means of ascertaining the distance of the sun. The idea had originated in rather vague form with Kepler, but was suggested more definitely by James Gregory in 1663. After Halley had observed the transit of Mercury in 1677, he realized the advantages of the method and published several papers urging preparations for observing the transit. He pointed out, says Berry, treating of this point in his Short History of Astronomy, that the desired result could be deduced from a comparison of the durations of the transit of Venus as seen from different stations of the Earth, i.e., of the intervals between the first appearance of Venus on the sun's disk and the final disappearance as seen at 2 or more different stations. He estimated, moreover, that this interval of time, which would be several hours in length, could be measured with an error of only about 2 seconds, and that in consequence the method might be relied upon to give the distance of the sun to about 1/500th part of its true value. As the current estimates of the sun's distance differed among one another by 20 or 30%, the new method, expounded with Halley's customary lucidity, was an enthusiasm not unnaturally stimulated astronomers to take great trouble to carry out Halley's recommendations. The results, however, were by no means equal to Halley's expectations. Immense trouble was taken by governments, academies, and private persons in arranging for the observation of the transits of 1761 and 1769. For the former, observing parties were sent as far as Tobolsk, St. Helena, the Cape of Good Hope, and India, while observations were also made by astronomers at Greenwich, Paris, Vienna, Uppsala, and elsewhere in Europe. The next following transit was observed on an even larger scale, the stations selected ranging from Siberia to California, from the Varanger Fjord to Otaheite, where no less famous a person than Captain Cook was placed, and from Hudson's Bay to Madras. The expeditions organized on this occasion by the American Philosophical Society may be regarded as the first of the contributions made by America to the science which has since owed so much to her. While the Empress Catherine of Russia bore witness to the newly acquired civilization of her country by establishing a number of observing stations on the soil of her empire. A variety of causes prevented the moments of contact between the disks of Venus and the Sun from being observed with the precision that had been hoped. The values of the parallax of the Sun deduced from the earlier of the two transits ranged between 8 minutes and 10 minutes, while those obtained in 1769, though much more consistent, still varied between 8 minutes and 9 minutes, corresponding with a variation of about 10 million miles in the distance of the Sun. The whole set of observations was subsequently very elaborately discussed in 1822 to 1824 and again in 1835 by Johann Franz Encke, who deduced a parallax of 8 minutes 57 seconds, corresponding with a distance of 95,370,000 miles, a number which long remained classical. The uncertainty of the data is shown by the fact that other equally competent astronomers have deduced from the observations of 1769 parallaxes of 8 minutes 0.8 and 8 minutes 0.9. End of section 16. Section 17 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler, Astronomy. Chapter 12, Part 2. The transits of Venus in 1874 and 1882 were memorable as the first in which photographic methods and the heliometer were applied, in addition to the older methods of time observation to measure the occasion of contact. The older methods left unavailable the remainder of the transit, but the heliometer made it possible to ascertain the planet's apparent position upon the Sun's disk at any time with great precision. In the transit of 1874, the most elaborate photographic measures ever undertaken until this time were carried out in the United States where conditions were most favorable. A continuous succession of photographs was made as the planet traveled across the Sun's disk, and various systems of reference enabled its position to be identified with great accuracy at any part of the transit. Yet results were hardly more valuable than those obtained by other methods. Hence, in 1882, the American observers modified their apparatus considerably from previous practice by employing the photographic plate and using the heliostat to reflect the Sun's rays through a telescope lens 5 inches in diameter and of 40-foot focal length. Doubtless better results could be obtained today with modern solar photographic equipment and dry plates. No great advances were recorded as the result of the numerous expeditions during these two transits. Elaborate expeditions were equipped particularly for the second of the two transits, and the observations which were voluminous were thoroughly and systematically discussed. The results were a somewhat larger value of the solar parallax, amounting to 8 minutes 0.857, or rather less than 93 million miles, as obtained by Newcomb after combining the heliometer with photographic measurements. As all measurements of this kind seem to be affected by some constant systematic error, it is the consensus of opinion among astronomers that other methods are more to be trusted in determining the solar parallax than those based on the transits of Venus. The great brilliancy of Venus is due to its relatively small distance from the Sun and the Earth and to its great reflecting power. The albedo of Venus, or the ratio of reflected to incident light, is 0.76. In other words, the planet reflects 3/4 of the light that falls upon it from the Sun, a proportion which is little exceeded by freshly fallen snow. This indicates that Venus is surrounded by a dense and cloudy atmosphere. Similar indications are given by the spectroscope, pointing to the existence of an atmosphere containing water vapor and generally similar to our own, but denser. This atmosphere of Venus, owing to its great refractive power, sometimes appears as a luminous ring in transits of the planet. From observations made at the transit of 1882, it has been computed that the density of the atmosphere of Venus is 1.8 that of the Earth's atmosphere, which produces a refractive displacement of 33 minutes. According to Medler's calculations, the atmosphere of Venus is 1.7 times as dense as that of the Earth. Many astronomers believe, therefore, that Venus is surrounded by a dense atmosphere into which the sun's rays do not penetrate to a depth sufficient to cause much loss by absorption, probably because they are reflected by opaque clouds. From this it would follow that the markings which have been observed on the disk of Venus through the telescope for centuries may be purely atmospheric. As the displacement of the surface markings of a planet when viewed through a telescope furnish the basis for estimates of the period of rotation, it may be that calculations so made are without justification. These markings of Venus are altogether different from those of any other planet. They are faint, indistinct, and apparently variable, for the drawings of Venus made by different observers before the advent of photography are very unlike. The first astronomer to observe any markings on Venus was Domenico Cassini, who discovered a bright spot in 1666. In the following year, he discovered a second spot from which he deduced a period rotation of about 24 hours, an estimate which was reduced to 23 hours and 22 minutes in Jacques Cassini's revision of his father's work. On the other hand, Bianchini, who studied the planet in 1726 and 1727, deduced from his observations a period of rotation equal to 24 days and 8 hours. Thus began the long and violent controversy in regard to the rotation of Venus. From more than 10,000 observations made between 1830 and 1841, De Vico computed a mean value of 23 hours, 21 minutes, and 23.93 seconds for the period of rotation of Venus. This value, furthermore, agrees very closely with the period of 23 hours deduced by Schroter from observations of the deformation of the horns of Venus 1788, 1793, and it has consequently been adopted in most treatises on astronomy. But in 1890, however, belief in the short period was shaken by Schiaparelli's discoveries. Before this, Schiaparelli had made this surprising announcement that the period of rotation of Mercury was equal to the period of its revolution about the Sun, and he now asserted that the same law governed the motions of Venus, a statement based on observations made in the winter of 1877-78, which showed that the bright spots then visible never varied their positions with respect to the terminator, or boundary line between the planet and its shadow. Observations made in 1895 gave additional support to the view that Venus rotates on her axis in the period of her revolution about the Sun, 225 days, and consequently always turns the same hemisphere toward the Sun, just as the Moon always presents the same face to the Earth. This theory, which on its announcement rested solely on Schiaparelli's authority, soon obtained strong independent support. It has apparently been completely confirmed by the observations made by Lowell at Flagstaff, Arizona in 1895-6. Lowell saw markings that have been seen by no other astronomer before or since, but the most surprising thing about his discoveries is that he saw no spots, but only bands or lines bearing a superficial resemblance to the canals of Mars. The whole configuration remained unchanged for hours, which could not be the case if the period rotation were only 24 hours. Furthermore, the markings remained fixed relatively to the terminator. Lowell denies the existence of clouds on Venus, although he finds in certain phenomena of twilight evidence of the presence of a very dense atmosphere. Many astronomers have refused to accept the conclusions of Schiaparelli, Perrotin, and Lowell, and have adhered to the theory of a short period of rotation. Schiaparelli's first announcement was vigorously disputed soon after its publication by the French astronomer Trouvelot. During his residence at Cambridge, Massachusetts, from 1875 to 1882, Trouvelot pointed out 17 changes in the markings which Schiaparelli regarded as fixed. Trouvelot regarded the bright spots on the limb of the planet as very high mountains rising above the atmosphere. The observed changes in the appearance of the horns of the crescent planet have also been ascribed to mountains. In the 18th century, Schroter announced the discovery of several mountains on Venus. In 1789, the southern horn of the crescent appeared blunted, and near it on the dark disk of the planet shone a bright peak, the height of which was estimated by Schroter as 117,000 feet, or 22 miles. Trouvelot deduced from his own observations a period of rotation of about 24 hours. It is very remarkable that two such experienced and trustworthy observers as Schiaparelli and Trouvelot could be led to such widely differing results from their frequent observations of the same object during the same period. It may be regarded as certain that the problem of the rotation of Venus cannot be solved by observing markings, which is not surprising if they are purely atmospheric phenomena. Sir William Herschel, who has justly been called the greatest observer of all time, doubted the reality of the markings of Venus and regarded them as atmospheric phenomena. But this view was not shared by any of his contemporaries. Beer and Mädler, who were also most excellent observers, studied Venus repeatedly in 1831 and later years, but they rarely, if ever, saw anything that deserved the name of a marking. Attempts have been made to solve the interesting and difficult problem of the rotation of Venus with the aid of the spectroscope, but these attempts have also failed to give a positive result. The effort was first made by the Russian spectroscopist Jelopolsky at Pulkowa Observatory. The spectrophotographic measurements, which were begun in 1900, indicated a short period of rotation. Although Jelopolsky did not regard the correctness of the result as assured, his authority led to the belief that the spectroscope had decided the question in favor of the short period. Then Lowell, who had deduced a period of 225 days from telescopic observations, sought confirmation for this value by the spectroscopic method. He first tested his new and delicate apparatus and method by applying them to Mars, and obtained for that planet a period of rotation of 25 hours and 35 minutes, which agrees fairly well with the known period 24 hours and 37 minutes. For Venus, Lowell's spectrophotographs give a rotational velocity of from 5 to 8 meters, 16.4 to 26.2 feet per second, which corresponds with a long period of rotation, though one much shorter than 225 days, for which the equatorial velocity would be about 2 meters, 6.56 feet per second. Neither of the results obtained at Pulkowa and at Flagstaff has yet been confirmed elsewhere. The spectroscopic method is too difficult to be attempted except by a particularly well-equipped and favorably situated observatory. The theory of slow rotation receives powerful support from certain arguments advanced by the distinguished English astronomer Sir George H. Darwin. The rotational velocity of every planet must be gradually diminished by tidal friction among its parts. In this way, the period of the Moon's rotation has been made equal to the period of her rotation about the Earth, and the rotational periods of Mercury and Venus may have been similarly lengthened to equality with their periods of revolution about the Sun, which exerts a far greater tidal action upon these inferior planets than upon the Earth. If Venus has already reached this stage, all the water on the planet must be accumulated in the form of ice on the dark and intensely cold hemisphere. Hence, as Antoniadi has pointed out, the presence of clouds and water vapor on the illuminated hemisphere casts grave doubt on the correctness of Schiaparelli's theory. The presence of clouds in the atmosphere of Venus is denied only by Lowell, who saw the peculiar canal-like markings distinctly whenever terrestrial atmospheric conditions permitted. No trace of markings, by the way, was seen by Hansky and Stefanik, who studied the planet in the summer of 1907 at the Mont Blanc Observatory, which is more elevated than Flagstaff, under very favorable atmospheric conditions, and deduced a period of rotation slightly less than 24 hours. So the problem of the rotation of Venus is still unsolved, although a majority of astronomers appear to share the view of Schiaparelli and Lowell. The hope that it can be solved by observing markings has proved illusory, and there is good reason to believe that the spectroscope will ultimately furnish the solution. Venus, in size, is almost identical with the Earth. Its diameter, expressed in miles, is 7,800, as compared with 7,920 for the Earth. Its circumference consequently amounts to 23,400 miles, as compared with 25,000 miles that of the Earth. The period of revolution around the Sun is 225 days. For many years, observers have been looking for satellites of Venus. Fontana, 1645, Cassini, 1672 and 1686, and Montaigne, 1761, among others, imagined that they had made such a discovery, but these have for many years been considered optical illusions. End of section 17.
Section 18 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 13, Part 1. The Earth. The conception of the Earth formulated by the ancients assumed it to be a flat disk floating on water, which idea persisted in some form or other despite various phenomena clearly impossible of explanation upon such a hypothesis. After some more or less vague speculation on the shape of the Earth by Thales, circa 640 to circa 546 BC, a clear and rational idea was advanced by Pythagoras, who flourished in the 6th century BC and taught that the Earth, in common with the heavenly bodies, was a sphere, and that it received no support at the center of the universe. The idea of the sphericity of the Earth was doubtless derived by analogy from the appearance of the moon. The theory became an established part of Greek science and philosophy, and consequently has continued to the present day, anticipating by some 2,000 years the acceptance of the belief in the Earth's rotation. In fact, the spherical form of the Earth figured prominently in Greek astronomy, and the division of the Earth into zones and the idea of poles was promulgated by the Alexandrian philosophers and even before their time. Indeed, not only did they realize the shape of the Earth, but also its size. Eratosthenes, 276 to 195 or 196 BC, whom we have already mentioned in our chapter on pre-telescopic work, made one of the first scientific measurements of the Earth, obtaining a result which must be considered the first good geodetic measurement. He found, from the application of simple geometry, that the angular distance of the Earth's surface between Alexandria and Cyrene must be 1/50th of the circumference of the Earth. Posidonius, who was born about the end of the life of Hipparchus, made a new measurement of the circumference of the Earth, much after the fashion of Eratosthenes, but reached a value too small. One of the crucial arguments for the sphericity of the Earth is that when a ship sails away, the hull first disappears from view, while the masts are visible. This was first advanced by Pliny, 23 to 79 AD. From the Greeks and Romans to the Arabs may be a far journey, but little was done in the study of the Earth until the Arab astronomers of Baghdad, under the patronage of Caliph al-Mamun, made a series of measurements of a meridian of the earth, which agreed with those of Ptolemy. These measurements virtually sufficed until Willebrord Snell, 1591 to 1626, a Dutch mathematician who had discovered the law of the refraction of light, made a series of measurements of the earth's surface from which he computed the length of a degree of a meridian to be about 67 miles, an estimate subsequently corrected to about 69 miles by one of his pupils, and differing but a few hundred feet from the value now accepted. A measurement by Richard Norwood, circa 1590 to 1675, of the distance from London to York, made in 1636, enabled a degree of latitude to be obtained with an error of less than half a mile, and finally Picard, in 1671, made a measurement of this quantity, which we have seen was sufficiently accurate to be used by Newton in computing the mass and motion of the earth and in demonstrating his law of gravitation. This outline shows that the spherical shape of the earth was constantly held in mind by scientists for about 2,500 years. Other views of the earth's shape also obtained. The idea of a flat earth had to be vigorously opposed by arguments founded on experiment, observation, and discovery. After the phenomenon of a disappearing ship, one of the most important of the arguments against the flatness of the earth's surface was based on the different elevations of the pole star in the sky, depending upon the position of the observer. Now, the pole star and the surrounding stars, though they may be at different heights in the sky, form the same pattern wherever on the earth's surface they are seen, thus showing that they are immensely distant and that lines from all points of the earth's surface directed to the pole star would be parallel or have the same direction. As one travels north, it is seen that the pole star sinks lower and lower in the heavens, or has a greater angular distance from our zenith. If the earth were flat, this would not be the case, for an angular distance of 7.5 degrees difference in the position of two stations 520 miles apart in a north and south line would mean that the star is only 3,450 miles distant, which is manifestly impossible. Furthermore, it is a well-known experience that in crossing the Atlantic from England to the United States, the sun by a watch rises an hour later for every 600 miles we travel west. If the earth were flat, the sun would rise at the same instant over its entire surface. To answer both these conditions, namely the sinking in the heavens of the pole star and the equal delays in the time of sunrise in traveling equal distances, a round globe is required. Still, the globular form of the earth was not accepted generally until after the historic voyage of Christopher Columbus and that epoch of exploration and discovery which resulted in the circumnavigation of the earth in 1519. After the demonstration of the sphericity of the earth came the determination of its exact figure by the systematic measuring of arcs of meridians. When the results were mathematically examined, the conclusion was reached that the earth was not a perfect sphere, but flattened at the ends, or in other words, that it was an oblate spheroid. Newton, in his Principia, published in 1687, showed from theoretical considerations that the earth bulged out at the equatorial regions. On the other hand, in the following century, in 1745, the Cassinis, who were leading astronomers of France and deeply interested in the measurement of the earth's surface, maintained that the earth was contracted at the equator and bulged at the poles, or in other words, was prolate. The difference in the two ideas being concisely expressed by Professor Moulton, who likens Newton's idea of the earth's figure to an orange and that of the Cassinis to a lemon. It is interesting that Newton's proof of the oblateness of the earth anticipated the direct observations of the astronomer and geodesist. Today, it can be demonstrated in simple form by means of observations of the time of vibration of a pendulum, such as are carried on systematically by such scientific agencies as the United States Coast and Geodetic Survey. It is possible to supply various mathematical proofs of the oblateness of the Earth in connection with its motions and with its relations to the Moon and to the solar system. But these hardly concern us in the present pages, and we may dismiss the matter with the assertion that the ellipticity of the Earth, as determined by Harkness in 1891, amounts to 1/300th as compared with a value of 1/295th established in 1866 by Colonel Clark of the English Ordnance Survey and accepted for many years as a standard, and 1/230th as was given by Newton for the ellipticity of a meridian section of this oblate spheroid. Clark's spheroid of 1866, which is generally adopted in geodetic and other computations, would give a radius at the equator of 3,963.307 miles and 3,949.871 miles at the poles, these figures having been slightly corrected in 1878 in the second place of decimals. The radius of the Earth is in many ways a fundamental measure, especially in astronomy, and for that reason its determination is a matter of no small importance. Thus, observations made with a view of finding the distance of the Moon when discussed and reduced simply give us this distance in terms of the equatorial radius of the Earth, so that to determine the distance in miles we must know the number of miles in the Earth's radius. As a consequence of the spheroidal shape of the Earth, a degree of latitude as well as of longitude varies with the point at which it is measured. Thus, at the equator, 1 degree of latitude is equal to 68.704 miles, but at the pole, a similar degree is equal to 69.407 miles. The difference in a degree measured on the parallels of latitude, which are small circles, is of course obvious, and while at the equator a degree of longitude amounts to 69.652 miles, at latitude 40 degrees, or approximately that of New York, 40 degrees 43 minutes, it would equal 53.431 miles, and at the North Pole it would decrease, of course, to 0. Newton, in his researches on gravitation, by comparing the attraction exerted by the Earth with that of the Sun and other bodies, was able to connect its mass with that of the planets and Sun. The problem of determining the mass of the whole Earth in terms of a given terrestrial body, that is, in tons, pounds, or kilograms, was indeed a serious one, and it was first attacked in Great Britain by Neville Maskelyne, 1732 to 1811, who was Astronomer Royal. If we know the volume of the Earth and its density, referred to some standard as water, air, or iron, it is, of course, easy to determine its mass. But the determination of its density is no less a problem than the determination of its mass directly. It is possible, of course, to compute the relative amount of water, but this gives only a small amount of the mere surface of the Earth. We can descend in mine shafts a mile or more and investigate the nature of the material, but this again affords no clue to the thousands of feet of materials below, so that an estimate of the average density based on such data cannot be considered at all trustworthy. Newton, taking into consideration the various elements of the Earth, estimated its density at between 5 and 6 times that of water. Maskelyne, however, bearing in mind the phenomenon of the deflection of the plumb line, observed by Bouguer and Le Condamine in their expedition to measure an arc of latitude in Peru, a phenomenon caused by the attraction of the mountain Chimborazo, selected the narrow ridge of Schehallien in Perthshire, and found that the attraction of the mountain caused a deflection of about 12 seconds on each side of the ridge. This attraction of the mountain, as compared with the attraction of the Earth on the plumb bob, enabled a value for the density of the Earth of about 4.5 times that of water to be obtained. It remained for the famous Cavendish experiment carried out by Henry Cavendish, 1731 to 1810, to substitute for the mountain a pair of heavy balls. This gave a value for the density of the earth of 5.5 times that of water, a value confirmed by numerous repetitions of Cavendish's classical experiment. Expressed in pounds, the mass of the earth is a little more than 13 billion, a figure that the human mind utterly fails to grasp. There must have been a time when the earth contained much more heat than at present. The sun is not supplying heat enough to make good the losses sustained by the globe. These losses must have been taking place over a period of countless years. One is forced to believe that not only once was our earth much hotter than at present, but that its temperature was a red heat. Going back still further, the now solid globe must have been actually a molten mass. Being a molten mass, it is not difficult to realize that it readily assumed a globular form on its journey through space. A falling drop of rain is a globe. A drop of oil suspended in a liquid with which it does not mix has a spherical shape. Therefore, if a mass of material as large as the earth were so soft that its individual particles obeyed the forces of attraction exerted by each part of the mass on all the other parts, it is quite obvious that it would assume a globular shape, especially under the influence of motion. If this great sphere were caused to rotate around its axis like a ball of clay on a potter's wheel, any lack of true sphericity would not only be overcome, but there would be a tendency for the molten body to bulge at the equator and flatten down at the poles, forming an oblate spheroid, such as by actual measurement the earth is found to be. Indeed, not only is the earth an oblate spheroid, but most of the planets which can be measured have become flattened at the poles for the same reason. In connection with the spherical shape of the earth, mention should be made of a recent theory which seeks to demonstrate that the shape of the earth is being transformed into a polyhedral form, or more exactly, that there is a tendency in the direction of its assuming the figure of a regular tetrahedron or four-sided figure, each of whose faces is triangular. This is manifested by the lithosphere or solid portion of the earth. The water is massed on the faces of such a tetrahedron, the force of gravity acting most powerfully at the center of each of the four surfaces. The tetrahedron hypothesis assumes that a more or less solid crust was formed when the earth was still perhaps in an approximately spheroidal form. As contraction occurred in the interior, the external shell proved too large. Hence, a different form has to be assumed, which it is asserted would be the tetrahedral. On each of the faces of such a tetrahedron, one of the four oceans would lie, the Arctic Ocean being assumed as the fourth for the region about the North Pole. The continents would correspond with North and South America, Euro-Africa, Asia-Australia, and Antarctica. This hypothesis is borne out in many respects by geological and other considerations. First advanced in the 70s of the 19th century by Lothian Green, the hypothesis has been put forward in recent years with further developments and attempts at its proof, so that it is considered as a tenable and possible explanation, though its absolute soundness has not been demonstrated. Recognizing and proving the spherical shape of the earth by no means explains the apparent motion of the sun, moon, and stars as regards the planet. As the nature of the solar system was developed by Copernicus and Newton, people were compelled to recognize that the earth revolved around the sun, and furthermore, that it rotated daily about its axis. These motions are necessary to explain various phenomena. For example, when a body moves in a circle, a force is needed to act on it, pulling toward the center proportionally to the square of the rate of spin, and proportionally to the distance. Every pound of mass in the moon would need a pull equal to about the weight of 3 ounces to keep it in a circle which it traveled around once in 24 hours. Every pound in the sun would need a pull about 3/4 of a hundredweight. The nearest fixed star would need a pull on every pound of about 9,000 tons. One cannot imagine that the earth could exert such forces, and so are obliged to think that the earth is revolving and not the sky. Final proof of the rotation of the earth was furnished in the middle of the last century by Foucault. His experiments were constantly repeated in physical laboratories and experimental lectures. From the dome of the Pantheon in Paris, he suspended a heavy ball by a fine cord and caused it to swing in a single plane. The path of the ball across the floor could be traced, and it was found that after it had been in vibration for some time, it was swinging in a different direction from that in which it had started. The reason was that the floor had revolved under the ball with the rotation of the earth. The daily rotation of the earth on its axis and its yearly rotation about the sun supply us with our means of measuring time. According to Professor Poynting, quote, "The earth is a clock. The line to the sun is the finger, and the sky is the face. But the earth is not a regular timekeeper. Our 24-hour day is only the average between successive noons or times when the sun is due south. If compared with a good clock, the sun is in parts of the year too soon and in other parts too late, sometimes as much as a quarter of an hour. This cannot be due to change in the earth's rate of spin, for to change a spin there must be either a force acting at one side of the center of gravity or a change of shape. The forces on the earth exerted by the sun and moon act almost exactly through the center of gravity, and so affect the rate of spin hardly at all. The earth does not change its shape sufficiently to account for the variation in the solar day. The variation in the solar day is due partly to the inclination of the earth's axis to the plane in which it moves around the sun, partly to variation of the earth's motion around the sun at different times of the year. The fixed stars keep good time, getting round in about 4 minutes less than 24 hours. By them, clocks are rated. Their day is the true time of one rotation of the earth." Unquote. End of section 18. Section 19 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 13. The Earth, Part 2. Among the movements of the earth, there is one that is so minute as to be of peculiar interest to the astronomer. It is a small displacement or wobbling of the axis of the earth or theoretical pole. This pole shifts its place through a circle of some few yards in diameter in the course of a period of somewhat over a year, and as a result there is a variation of latitude on the earth's surface. This was discovered first in 1884 and 1885 by Dr. Küstner at Berlin, and after observations made at various stations by members of the International Geodetic Association in 1888, it was found that this synchronous variation was occurring in a periodic manner at a number of stations. The general nature of the occurrence was defined by Professor S.C. Chandler in 1891, who stated that the pole of the earth might be supposed to describe a circle with a radius of 30 feet in a period of 14 months. One reason assigned for this phenomenon is a change in the distribution of mass due to the temporary occurrence of heavy falls of snow or rain limited to one continent, or to the transportation of great bodies of water and air from place to place by atmospheric or sea currents, so that the globe is made slightly lopsided and temporarily to forsake its normal axis. Also, it has been supposed that the earth is not absolutely rigid. As a quasi-plastic mass, it would yield to certain strains, which tend to protract the time of circulation of the displaced pole. In fact, in all consideration of the various phenomena of gravitation and tides, we have to recognize that in practice the astronomer of today is not dealing with the theoretically rigid body of Newton and the earlier mathematicians. One of the important conditions of the rotation of the earth is that it moves around an axis which is not vertical, but which is inclined toward the plane of its orbit. Dolmage, in his volume Astronomy of Today, tells us that, quote, if the axis of the Earth stood straight up, so to speak, while the Earth revolved in its orbit, the Sun would plainly keep always on a level with the equator. This is equivalent to stating that in such circumstances, a person at the equator would see it rise every morning exactly in the east, pass through the zenith, that is the point directly overhead of him at midday, and set in the evening, due in the west. As this would go on unchangingly at the equator every day throughout the year, it should be clear that at any particular place upon the earth, the sun would, in these conditions, always be seen to move in an unvarying manner across the sky at a certain altitude, depending upon the latitude of the place. Thus, the more north one went upon the earth's surface, the more southerly in the sky would the sun's path lie, while at the North Pole itself, the sun would always run round and round the horizon. Similarly, the more south one went from the equator, the more northerly would the path of the sun lie, while at the South Pole it would be seen to skirt the horizon in the same manner as at the North Pole. The result of such an arrangement would be that each place upon the earth would always have one unvarying climate, in which case there would not exist any of those beneficial changes of season to which we owe so much. The changes of season which we fortunately experience are due, however, to the fact that the sun does not appear to move across the sky each day at one unvarying altitude, but is continually altering the position of its path, so that at one period of the year it passes across the sky low down, while at the other it moves high up across the heavens and is above the horizon for a much longer time. Actually, the sun seems little by little to creep up the sky during one half of the year, namely from midwinter to midsummer, and then just as gradually to slip down it again during the other half, namely from midsummer to midwinter. It will therefore be clear that every region of the earth is much more thoroughly warmed during one portion of the year than during another, that is, when the sun's path is high in the heavens than when it is low down. Once more, we find appearances exactly the contrary from the truth. The earth is, in this case, the real cause of the deception, just as it was in the other cases. The sun does not actually creep slowly up the sky and then slowly dip down it again, but owing to the earth's axis being set aslant, different regions of the earth's surface are presented to the sun at different times. Thus, in one portion of its orbit, the northerly regions of the earth are presented to the sun, and in the other portion, the southerly. It follows, of course, from this, that when it is summer in the northern hemisphere, it is winter in the southern and vice versa. The fact that in consequence of this slant of the earth's axis, the sun is for part of the year on the north side of the equator and part of the year on the south side leads to a very peculiar result. The path of the moon around the earth is nearly on the same plane with the earth's path around the sun. The moon, therefore, always keeps to the same regions of the sky as the sun. The slant of the earth's axis thus regularly displaces the position of both the sun and the moon to the north and south sides of the equator respectively in the manner we have been describing. Were the earth, however, a perfect sphere, such change of position would not produce any effect. At present, the north pole of the heavens is quite close to a bright star in the tail of the constellation of the Little Bear, which is consequently known as the pole star, but in early Greek times it was at least 10 times as far away from this star as it is now. After some 12,000 years, the pole will point to the constellation of Lyra and Vega. The most brilliant star in that constellation will then be considered as the pole star. This slow twisting of the earth is technically known as precession, or the precession of the equinoxes. We have seen that the orbit of the earth is an ellipse and that the sun is situated at what is called the focus, a point not in the middle of the ellipse, but rather toward one of its ends. Therefore, during the course of the year, the distance of the earth from the sun varies. The sun, in consequence of this, is about 3 million miles nearer to us in our northern winter than it is in our northern summer, a statement which sounds somewhat paradoxical. This variation in distance, large as it appears in figures, cannot, however, be productive of much alteration in the amount of solar heat which we receive, for during the first week in January, when the distance is least, the sun only looks about 1/18 broader than at the commencement of July, when the distance is greatest. The great disparity in temperature between winter and summer depends, as we have seen, upon causes of quite another kind, and varies between such wide limits that the effects of this slight alteration in the distance of the sun from the earth may be neglected for practical purposes." End quote. The most striking effect of gravitation in its universal aspect is seen on the earth in the case of the tides, which are due to the attraction of the moon on the earth and especially on the waters of its ocean. While the ancients could not explain the cause of the daily change in the tides, the phenomenon was obvious to all mariners or those dwelling by the sea or even on great rivers. The connection of the moon with this phenomenon, it is claimed, was understood as early as 1000 B.C. by the Chinese, for at full and new moon exceptionally high tides were observed, and the name of spring tides was applied as contrasted with the minimum high water which was observed at the neap tides at the second and fourth quarters of the moon. Not only the Chinese, but the Greeks and Romans noticed this same phenomenon, and Julius Caesar in his commentaries tells us that when he was embarking his troops for Britain, the tide was high because the moon was full, while both Pliny and Aristotle connect the time of high water with the age of the moon. The connection between the moon and the tide was thus early established and practically applied by navigators, who were quick to realize the nature of the phenomenon, even though they and the astronomers were unable to present any satisfactory explanation. A general explanation of the tides as due to the disturbing action of the moon and sun, especially the former, was put forward by Newton. Newton's explanation, as described by Berry in his short History of Astronomy, was as follows, quote, "If the earth be regarded as made of a solid spherical nucleus covered by the ocean, then the moon attracts different parts unequally, and in particular, the attraction measured by the acceleration produced on the water nearest to the moon is greater than that on the solid earth, and that on the water farthest from the moon is less. Consequently, the water moves on the surface of the earth, the general character of the motion being the same as if the portion of the ocean on the side toward the moon were attracted, and that on the opposite side repelled. Owing to the rotation of the earth and the moon's motion, the moon returns to nearly the same position with respect to any place on the earth in a period which exceeds a day by, on the average, about 50 minutes, and consequently Newton's argument showed that low tides or high tides due to the moon would follow one another at any given place at intervals equal to about half this period, or in other words, that two tides would in general occur daily, but that on each day any particular phase of the tides would occur on the average about 50 minutes later than on the preceding day, a result agreeing with the observation. Similar but smaller tides were shown by the same argument to arise from the action of the sun, and the actual tide to be due to the combination of the two. It was shown that at new and full moon, the lunar and solar tides would be added together, whereas at the half moon they would tend to counteract one another, so that the observed fact of greater tides every fortnight received an explanation. A number of other peculiarities of the tides were also shown to result from the same principles." End quote. From Newton's time to the present, the tides have supplied material for astronomical and mathematical research, so that through the efforts of many astronomers and other scientists, their theory and occurrence are now well understood, and the various governments make ample provision through hydrographic offices and otherwise to provide such information for mariners. In the theoretical discussion in modern times, one name stands out prominently, that of Sir George H. Darwin of England, whose researches on the tides of the earth have developed to a point where they have a most important bearing on cosmical theory. It is desirable here to outline the chief features of tides in their everyday occurrence. The term flood tide is applied to the rising water which reaches high water mark at the moment when the tide is highest, while in falling the tide is said to ebb until low water or the lowest mark is reached. Near the times of new and full moon occur the spring tides, which are the highest tides of the month, as distinguished from the neap tides, which are the smallest, occurring when the moon is in quadrature. The relative heights of spring and neap tides being about as 7 to 4. At the time of spring tides, the interval between the corresponding tides of successive days is less than the average value of 24 hours and 51 minutes, and the tides are said to prime, the interval amounting to about 24 hours and 38 minutes, while at neap tides, the interval increases to 25 hours and 6 minutes, and then the tides are said to lag. The highest tides of all occur when the new or full moon at the time the moon is in perigee, especially as this takes place about January 1st when the earth is nearest to the sun. Not only are the tides interesting for their relation to navigation, but on account of their intimate connection with the motion of the earth. The daily movement of the tides is a drag on the energy of our planet and is acting to cut down its speed of rotation. If the speed of rotation of the earth diminishes, it is obvious that our day is being lengthened, that today is longer than yesterday, and that tomorrow will be longer than today, even though these increases are all but inappreciable in the time that the human mind can fathom. Sir Robert Ball, in his Story of the Heavens, summarizes the variation wrought by the tides in the following paragraph, quote, "Let us take a glance back into the profound depths of times past and see what the tides have to tell us. If the present order of things has lasted, the day must have been shorter and shorter the farther we look back into the dim past. The day is now 24 hours, but it was once 20 hours, once 10 hours, and once 6 hours. How much farther can we go? When the 6 hours is past, we begin to approach a limit which must at some point bound our retrospect. The shorter the day, the more is the earth bulged at the equator. The more the earth is bulged at the equator, the greater is the strain put upon the materials of the earth by the centrifugal force of its rotation. If the earth were to go too fast, it would be unable to cohere together. It would separate into pieces, just as a grindstone driven too rapidly is rent asunder with violence. Here, therefore, we discern in the remote past a barrier which stops the present argument. There is a certain critical velocity, which is the greatest that the earth could bear without risk of rupture. But the exact amount of that velocity is a question not very easy to answer. It depends on the nature of the materials of the earth. It depends upon the temperature. It depends upon the effect of pressure and on other details not accurately known to us. An estimate of the critical velocity has, however, been made, and it has been shown mathematically that the shortest period of rotation that the earth could have without flying into pieces is about 3 or 4 hours. The doctrine of tidal evolution has thus conducted us to the conclusion that at some inconceivably remote epoch, the earth was spinning around its axis in a period approximating to 3 or 4 hours." End quote. The existence of tides in the solid earth as well as in the ocean was first indicated by Lord Kelvin in 1867. The first numerical estimate of the amount of the tidal oscillations of the solid earth was made by Sir George H. Darwin in 1882 and was based on an indirect method and resulted from observation of the tides of the ocean. Further indirect methods were successfully applied later with more complete data. Sir George H. Darwin has expressed the opinion that we may now feel confident that the earth yields to the tidal forces to the same degree as would a steel globe. The amazing accuracy of Dr. Hecker's recent observations, 1908, are marked by certain collateral considerations, among which may be mentioned the flexure of coastlines due to the varying pressure of oceanic tides and the effects of high and low barometric pressure in bending the earth's surface. It is impossible to give an accurate measurement of the amount of the vertical motion of the Earth's surface, but it is probable that at spring tides in this latitude, the surface of the solid Earth moves up and down through about 6 inches. End of section 19.
Section 20 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Fred Abood. The Science, History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 14. The Moon. Part 1. That the Moon is the nearest the Earth of all the heavenly bodies is one of the most obvious facts which confront the stargazer. Its regular motion must have been early appreciated by primitive man, after he had realized that the rising and setting of the sun marks regularly recurrent intervals of time. As he was able to reflect upon his observations and properly to coordinate them, he doubtless noted the connection between the form of the moon and its position in the sky with respect to the sun. For by keeping count with pebbles, or rude notches cut in a stick, he would learn that the interval of time between recurring full moons was always the same, and that the series of changes he could observe followed in regular order. Thus, when the moon appeared after sunset near the place where the sun had disappeared, he saw a thin crescent, the hollow side of which was turned away from the sun. A little later, the moon set. The next night he observed the moon, further from the sun, with a thicker crescent, and noted also that it set later, an effect that gradually increased until the semicircular disk, with the flat side turned away from the sun, was seen in rather less than a week after the first appearance of the crescent. In another week, the semicircle enlarged to a complete disk, and the moon rose about sunset and set about sunrise, being in a direction nearly opposite to that of the sun. From this time on, the size again diminished. The semicircular form was seen once more with the flat side still turned away from the sun, and toward the west instead of the east, as the moon approached the sun on the other side, rising before it and setting in the daytime. Again he saw the crescent, and marked that the time of rising approached that of sunrise, until the moon became altogether invisible. 2 or 3 nights intervened, and the new moon reappeared, whereupon the whole series of changes was repeated. In other words, this primitive man must have formulated a lunar month. All ancient records recognize this lunar month of 29.5 days, and that interval must have been adopted long before the year. By the time of Chaldean and Egyptian astronomy, however, the year was known, so that the first conception of the lunar month is lost in the mists of antiquity. The Chaldeans studied the motions of the sun and the moon. Their calendar records, which they seem to have maintained with considerable care, enabled them to discover that eclipses occurred after a period known as the Saros, consisting of 6,585 days. The nature of the moon was, of course, to them a mystery. It was known to move around the sky. The Babylonians supposed that, having a bright and a dark side, the different phases were caused by the bright sides coming more and more into view during its movement around the sky. In the 7th century, Pythagoras taught more correctly that the moon, like other heavenly bodies, was spherical, and that it was bright because it received the light of the sun. The phases, he rightly judged, were due to a greater or less amount of the illuminated half turned toward us, and the curve forming the boundary between the bright and dark portions of the moon was to him conclusive evidence of a spherical shape. He was later supported in his theory by Aristotle, who made a similar, clear and definite statement of the reason for the phases of the moon. Perhaps the first systematic study of the moon was that of Aristarchus, a famous member of the Alexandrian school, who flourished in the first half of the 3rd century and wrote a treatise on the magnitudes and distances of the sun and moon, which still survives. Taking the moon when it was half full, so that a line drawn to it from the sun made a right angle with the line from the moon to the earth, by measuring the angle between the moon and the sun, he was able to determine the ratio of the sides of this triangle and the relative distance of the moon and the sun from the earth. While the method of Aristarchus was ingenious, yet the result he obtained, that the sun was 18 to 20 times as far distant as the moon, was sadly in error, for the actual distance is nearly 400 times. Still, the difficulties in the way of accurate observation were enormous for lack of proper instruments. Aristarchus also took advantage of the solar eclipse to ascertain the distances of these two bodies, and reasoned correctly that when the moon sometimes rather more than hides the surface of the sun, and sometimes does not quite cover it, their diameters must vary as their real distances. He even obtained, by eclipse observations, a value for the diameter of the moon in terms of that of the earth. What would have been an excellent approximation was marred, however, by an incorrect estimate of the apparent size of the moon, which he took as 2 degrees instead of 1/2 degree. Nevertheless, this work was an important advance in practical astronomy. It paved the way for Hipparchus, who discussed the motions of the moon, motions which, long before his time, were known to be irregular and much more complicated than those of the sun. The path of the moon is always changing, and its motions are subject to variation. Hipparchus notes that the part of the moon's path in which the motion is most rapid is not always in the same position on the celestial sphere, but moves continuously. He was able to realize the different motions of the moon, to distinguish the various months based upon them, and to employ the Chaldean and other early eclipse observations for determining the position of the moon at various earlier epochs. Hipparchus really evolved a most complicated set of motions. He was aware of the shortcomings of his theory, but was unable to reconstruct it in a satisfactory manner. Following out the eclipse method of Aristarchus, Hipparchus made a determination of the relation between the distances of the sun and moon, measuring their angular diameters, and found that the distance of the moon is nearly 59 times the radius of the earth. Combining this figure for the distance of the sun with that of Aristarchus, a value of 1,200 times the radius of the earth was obtained, which value was employed for many centuries. Ptolemy, in the 4th book of the Almagest, discusses the length of the month with the theory of the moon, and makes the important announcement of a further inequality in the moon's motion, which Hipparchus had only suspected, and which was due in large part to its position with respect to the sun. This was later termed evection, and involved a still further complication of the mathematical computations of Hipparchus, because it meant the use of an epicycle and a deferent, which was itself a moving eccentric circle, the center of which revolved around the Earth. Ptolemy's mathematics and ingenuity were able to fit his theory to observations. Although his work showed many inconsistencies which, great as he was unable to control, nevertheless it represented a notable development in astronomy. To Ptolemy is due the parallax method for obtaining the distance of the moon by observing its direction from 2 points on the Earth's surface, and by finding the distance between these 2 points in terms of the Earth's radius. This distance of the moon, he estimated, was 59 times the radius of the Earth. With this value, according to the method of Hipparchus just mentioned, he computed the distance from the Earth to the Sun. He found that the distance was 1,210 times the radius of the Earth, which value was equally in error as compared with the modern figure. The actual distance is about 20 times this amount. So readily were the motions of the moon observed, and so carefully were the records maintained, that even at an early date, much was known about its motions. These data enabled much calculation of the moon's motion to be carried on, so that early mathematical astronomy dealt with the moon in no small degree. Various irregularities of its motion and appearance were discussed, and practically all of the notable astronomers made some contributions to our knowledge of the satellite. Even an outline of these discussions would lead the reader far afield into the depths of mathematics, for which reason it is possible to mention only a few of the important researches and to indicate merely their general nature. The study of the moon had a practical importance, however, as lunar positions were early used to determine longitude in navigation, and lunar tables were calculated by government and other astronomers. Nowhere was there more interest manifested in the problem of the motion of the moon than at Greenwich Observatory, where the matter had always been a specialty of that institution. It is a curious fact, states the late Professor Newcomb in his Reminiscences of an Astronomer, that while that observatory supplied all the observations of the moon, the investigations based upon these observations were made almost entirely by foreigners, who also constructed the tables by which the moon's motion was mapped out in advance. The most perfect tables made were those of Hansen, the greatest master of mathematical astronomy during the middle of the century, whose tables of the moon were published by the British government in 1857. They were based on a few of the Greenwich observations from 1750 to 1850. The period began with 1750 because that was the earliest at which observations of any exactness were made. Only a few observations were used, because Hansen, with the limited computing force at his command, only a single assistant, I believe, was not able to utilize a great number of the observations. The rapid motion of the moon, a circuit being completed in less than a month, made numerous observations necessary, while the very large deviations in the motion produced by the attraction of the sun made the problem of the mathematical theory of that motion the most complicated in astronomy. Thus it happened that, when I commenced work at the Naval Observatory in 1861, the question whether the moon exactly followed the course laid out for her by Hansen's tables was becoming of great importance. For a year or two our observations showed that the moon seemed to be falling a little behind her predicted motion. But this soon ceased, and she gradually forged ahead in a much more remarkable way. In 5 or 6 years it was evident that this was becoming permanent. She was a little farther ahead every year. What could it mean? To consider this question, I may add a word to what I have already said on the subject. In comparing the observed and predicted motion of the moon, Mathematicians and astronomers, beginning with Laplace, have been perplexed by what are called inequalities of long period. For a number of years, perhaps half a century, the moon would seem to be running ahead, and then she would gradually relax her speed and fall behind. Laplace suggested possible causes, but could not prove them. Hansen, it was supposed, had straightened out the tangle by showing that the action of Venus produced a swinging of this sort in the moon. For 130 years, she would be running ahead, and then for 130 years, more falling back again, like a pendulum. Two motions of this sort were combined together. They were claimed to explain the whole difficulty. The moon, having followed Hansen's theory for 100 years, would not be likely to deviate from it. Now it was deviating. What could it mean? Taking it for granted, on Hansen's authority, that his tables represented the motions of the moon perfectly since 1750, there was no possibility of learning anything from observations before that date. As I have already said, the published observations with the usual instruments were not of that refined character which would decide a question like this. But observations of stars, which might be available, and which had been made in many instances, would have an important bearing on this work. For if an oscillation or passage of the moon between a star and the earth occurred, and its time registered, the path of the moon in the heavens and the time at which it arrives at each point of the path would be determined if the time of the oscillation was known within 1 or 2 seconds. Professor Newcomb continues, "It was not until after the middle of the century, 17th, when the telescope had been made part of astronomical instruments for finding the altitude of a heavenly body, and after the pendulum clock had been invented by Huygens, that the time of an oscillation could be fixed with the required exactness. Thus it happens that from 1640 to 1670, somewhat coarse observations of the kind are available, and after the latter epoch, those made by the French astronomers became almost equal to the modern ones in precision. The question that occurred to me was, is it not possible that such observations were made by astronomers long before 1750? Searching the published memoirs of the French Academy of Sciences and the Philosophical Transactions, I found that a few such observations were actually made between 1660 and 1700. I computed and reduced a few of them, finding with surprise that Hansen's tables were evidently much in error at that time. But neither the cause, amount, or nature of the error could be well determined without more observations than these. Was it not possible that these astronomers had made more than they had published? The hope that material of this sort existed was encouraged by the discovery at the Pulkowa Observatory of an old manuscript by the French astronomer Delisle, containing some observations of this kind. I therefore planned a thorough search of the old records in Europe to see what could be learned. By good fortune, suitable observations were found at the Paris Observatory, and their relations and the method of making were studied, and everything necessary was copied. This work took some 6 weeks, but Professor Newcomb says, "The material I carried away proved the greatest find I ever made." 3 or 4 years were spent in making all the calculations I have described. Then it was found that 75 years were added, at a single step, to the period during which the history of the moon's motion could be written. Previously, this history was supposed to commence with the observations of Bradley at Greenwich, about 1750. Now it was extended back to 1675, and with a less degree of accuracy, 30 years farther still. Hansen's tables were found to deviate from the truth in 1675, and subsequent years to a surprising extent, but the cause of the deviation is not entirely unfolded, even now. One curious result of this work is that the longitude of the Moon may now be said to be known with greater accuracy through the last quarter of the 17th century than during the 90 years from 1750 to 1840. The reason is that, for this more modern period, no effective comparison has been made between observations and Hansen's tables. End of section 20. Section 21 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Fred Abood. The Science, History of the Universe, Volume 1. Edited by Francis Rolt Wheeler. Astronomy. Chapter 14. The Moon. Part 2. As the Moon rotates around the Earth, while the Earth is passing in its orbit about the Sun, it will be obvious that twice in its journey the Sun must come into a line of intersection of the Moon's orbit with that of the Earth. When this happens at the time of full moon, the Earth will lie directly between the Moon and the Sun, so that the light from the Sun is intercepted and a shadow is formed on the Moon's surface. Sometimes the Moon only partially enters the Earth's shadow, and then the eclipse, as this phenomenon is termed, is partial. If, however, the Sun is situated on the line of intersection at the time of new moon, then the Sun will be eclipsed, and a solar eclipse so rich in astronomical significance occurs. Solar eclipses have been discussed elsewhere, and their importance explained. Lunar eclipses, besides enabling us to check the motions of the Moon and furnishing an interesting spectacle, afford little scientific information. When the black shadow on the Moon is first detected in the case of a total lunar eclipse, it is interesting to watch its encroachment until the entire surface of the satellite is covered. Even the Moon, on which no direct sunlight can fall, is often visible, glowing with a copper-colored hue, sufficiently bright to enable several of the markings on the surface to be seen. This is due to refraction of the atmosphere, which bends the sunbeams that have just grazed the Earth and permits them to fall within the shadow. In their journey through the denser atmosphere, they have become rich in red rays, which gives to the disk a ruddy or copper-like hue, analogous to that of the Sun at sunrise or sunset. Whether the eclipse of the Moon is total or partial depends on the extent to which it passes into the shadow of the Earth, as the accompanying diagram will indicate clearly. Lunar eclipses are useful to the astronomer for determining the length of the synodic month, and also for determining the temperature to which the Moon has been raised, for when it enters the shadow, all direct light from the Sun is cut off and the Moon becomes cold very rapidly. Furthermore, the position of the Moon with respect to the stars can be determined on such occasions with great accuracy. Like solar eclipses, eclipses of the Moon can be predicted with high precision, and they are regularly announced in almanacs and ephemerides. The Moon always presents the same face to the Earth, a phenomenon discovered by Galileo. It must follow that the Moon rotates on its axis once in the same number of seconds that it requires for a revolution around our planet. This is explained by the fact that tides on the Moon, as in the case of the Earth, have lengthened the period of rotation by their braking action. At a time when the moon was still a hot, semi-molten mass, the attraction of the Earth produced great tides, not tides of water, but tides of molten rock. These tides on the moon checked its rotational velocity and eventually constrained the moon to rotate on its axis in precisely the same period as that which it requires to revolve around the Earth. All this happened eons ago. There is no longer evidence of any tidal action because the moon is frozen. Although there can hardly be tides on the moon, yet there may be tides in the moon. It may be that the interior of the moon is still hot enough to retain an appreciable degree of fluidity, writes Sir Robert Ball. And if so, the tidal control would still retain the moon in its grip. But the time will probably come, if it have not come already, when the moon will be cold to the center, cold as the temperature of space. If the materials of the moon were what a mathematician would call absolutely rigid, there can be no doubt that the tides could no longer exist, and the moon would be emancipated from tidal control. It seems impossible to predict how far the moon can ever conform to the circumstances of a rigid body, but it may be conceivable that at some future time the tidal control shall have practically ceased. There would then be no longer any necessary identity between the period of rotation and that of revolution. A gleam of hope is thus projected over the astronomy of the distant future. We know that the time of revolution of the moon is increasing, and so long as the tidal governor could act, the time of rotation must increase sympathetically. There will then be nothing to prevent the rotation remaining as at present, while the period of revolution is increasing. The privilege of seeing the other side of the moon, which has been withheld from all previous astronomers, may, thus in the distant future, be granted to their successors. While study of the moon and its motions continued, a beginning was made in the Renaissance to examine the surface of this satellite. Leonardo da Vinci, 1452 to 1519, was the first to explain correctly the dim illumination seen over the rest of the surface of the moon when the bright part was only a thin crescent. This he maintained is due to the earthshine, or slight illumination of the moon by light reflected from the earth, just as moonshine is able to illuminate the earth. Galileo's lunar observations through his telescope were epoch-making. Not only was he able to disprove many common conceptions of the nature of the satellite and its surface, but also to present a mass of evidence of a positive character. In spite of the familiar dark markings, the moon was really supposed to be a smooth sphere. After the introduction of the telescope, however, it was recognized by Galileo that the surface of the Earth's satellite was dotted with various inequalities, which he assumed to be mountains, valleys, and seas. Thus he correctly accounted, in part at least, for the unevenness of the surface. He was not content with mere observation of the features of the moon's surface, but measured the height of some of the more conspicuous lunar mountains, and obtained for them an estimated elevation of 4 miles, a figure which agrees fairly well with modern estimates. Having seen and measured mountains on the moon's surface, it seemed natural that there should be water. The large dark spots he erroneously regarded as seas, although he was not responsible for the corresponding names applied to these supposed expanses of water by some of his successors, and still preserved in lunar maps. The chief marks of astronomical progress, as revealed by Galileo's observation of the moon, were that it was a body in many respects similar to the Earth, that it was not a perfect sphere, and that there is no fundamental difference between celestial bodies and our own Earth, either in their motions or in their general nature, which was important in the final establishment of the Copernican theory. One other discovery of Galileo's in connection with the moon is of great importance. It had been known for many years that as the moon revolved around the Earth, the same markings were constantly seen. With the telescope, these markings could be studied so much more distinctly that it occurred to Galileo to ascertain whether there was any change in the moon's disk, or whether its appearance was always exactly the same. He found that as the moon moves in its orbit around the Earth, that slight changes are seen in its appearance. In other words, small portions of the hemisphere alternately on its northern and southern half are exposed. The simplest of the motions of the moon in this way subsequently came to be known as librations. Kepler, in his epitome of the Copernican astronomy, demonstrated that his planetary laws applied to the motion of the moon around the Earth, despite irregularities which introduced enormous complications. In this work, however, he devotes much attention to the theory of the moon, explaining in considerable detail both evection and variation. Galileo established the fact that the moon was similar to the Earth in many respects. The analogy was carried somewhat further by certain of the pioneer workers with large telescopes. Even Herschel held that because the moon closely resembled the Earth, it might be a suitable habitat for human beings. The dark spots once taken for seas and bearing that name on lunar maps are, in reality, lava, while the craters which dot the surface of the satellite, with one or two possible exceptions, belong to volcanoes long since extinct. The dark lines once known as rills, which it was assumed were rivers, are plainly without water. If there is a lunar atmosphere, its density must be very small, in fact less than that of the atmosphere far above the Earth. That there is a very rare lunar atmosphere seems to be probable. In fact, the assumption of an atmosphere is necessary for the explanation of certain phenomena. After Galileo's lunar studies, the next important work was that of John Hevel of Danzig, 1611 to 1687, who published in 1647 his Selenographia, in which not only the text, but the plates were prepared by him. Here he systematically describes the names and chief features of the moon, the immense craters and seas, employing many names taken from the Earth, such as Apennines, Alps, and Mare Serenitatis for the Pacific Ocean, all designations still found on modern lunar maps. Not all of his names have survived. John Baptiste Riccioli, 1598 to 1671, in a treatise on astronomy called The New Almagest, 1651, gave to various mountains and craters the names of distinguished men of science and philosophers. Hence the names of Plato, Archimedes, Tycho, and Copernicus are found on lunar maps. These names have survived in considerable number. More modern map makers, such as Beer and Maedler, whose map was published in 1837, and Schmidt of Athens, who published a map of the moon 7 feet in diameter in 1878, have carried out this idea. Modern astronomers are likewise honored, with the names of various points represented on the maps. For the origin of the moon, the mind must be forced to look back millions and millions of years to a time when our Earth existed in a very different form. Then it was not a solid mass, but a globe of molten material on which floated a crust, perhaps some 35 miles thick. It rotated not in a period of 24 hours, the present day's length, but at a terrific velocity which may have made the day some 3 hours in length. Such a speed of revolution naturally produced a most powerful centrifugal force. One day a cataclysm occurred. 5,000 cubic millions of miles of matter were thrown off into space. Thus the moon was born. A great scar was left on the surface of the Earth, a scar which, in the opinion of Professor William H. Pickering, is the basin of the Pacific Ocean. After this rending of the Earth, the remaining parts of the crust, afloat on the liquid interior, were split along irregular lines into two pieces, which drifted apart and were filled by the waters of the Atlantic and Pacific Oceans. This theory of Pickering's is diametrically opposed to that of Professor T.J.J.C., who claims that the moon is in reality a planet captured by the Earth in its wanderings through space, and that all satellites have been thus captured. Whatever the origin of the moon, it is the largest of all the planetary satellites, yet smaller in mass than the Earth, from which it is separated by a distance that varies between 222,000 and 253,000 miles. Its gravity is equal to about 1/6 that of the Earth, for which reason the same amount of energy acting, for example, in a volcanic upheaval produced mountains higher than those on the Earth. This mass of the moon is about 1/80th that of the Earth, or 73 trillion tons. The accompanying diagram shows the comparative size of the Earth and the moon. The diameter of our planet is 7,914 miles, while that of the moon is 2,160 miles, so that the diameters stand very nearly in the relation of 4:1, while the superficial area of the moon is equal to about 1/13th part of the surface of the Earth. The average distance of the moon from the Earth is also fairly constant, and the average fluctuations do not exceed more than about 13,000 miles on either side of its mean value of 239,000 miles. The moon is essentially a dead planet in the eyes of most astronomers. Its fires long since have been extinguished. It is a great globe of chilled slag. Its craters have no counterpart on the Earth. The lunar crater is a great circular plain, 50 or even 100 miles in diameter, around which rises a precipice perhaps 5 or 10,000 feet, while in the center there may be a hill or two about half as high. Thousands of these volcanoes are visible in the telescope. How these craters were formed is a puzzle. Some astronomers hold that they mark the impact of countless meteorites. Others assume them to be the product of gigantic bubbles in a once molten mass that burst. Again, it is claimed that they are volcanoes resembling those of the Earth. Most astronomers tell us that the craters have long been dead, that the moon has had for centuries no atmosphere, and therefore cannot have water or support plant or animal life. Professor William H. Pickering, however, tells us of an exceedingly rare lunar atmosphere and maintains that the moon's craters are not all extinct. He even claims that certain great white expanses are snow and ice, and furthermore, that there is evidence of the growth and decay of vegetation. To support his views of vanishingly feeble volcanic activity, he calls attention to the little crater named Linne, after the famous naturalist Linnaeus. In modern times, this crater has unquestionably undergone changes. Only a few centuries ago, it was described on the old maps as a crater of moderate size, and later as a very small, round, brilliant spot. A dead volcano cannot alter its shape. If there are still a few intermittently active volcanoes, they must expel water and carbonic acid gas, judging by earthly volcanoes. But water cannot be found on the moon as a liquid, for the temperature of its surface is probably not far from 460 degrees Fahrenheit below zero. Many of the elevated peaks are capped with a silver glow, which also characterizes the lining of the craterlets. In Pickering's eyes, that white sheen is snow. He believes also in accumulations of snow and ice at the poles. If carbonic acid is expelled by lunar volcanoes, it must cling to the moon with great tenacity because of its weight. Since it is the food of plant life, it may possibly support vegetation on the moon. Professor Pickering sees in variable dark spots on the planet organic life resembling vegetation. He figures that since certain lichens grow in certain regions of the Earth where the temperature never rises above the freezing point, there is no reason why that vegetation may not flourish on the moon's surface. End of section 21.
Section 22 of the Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 1. Edited by Francis Rolt Wheeler. Astronomy. Chapter 15. Mars, Part 1. Mars is another instance of a celestial body whose discovery long antedates written history, for which reason it is natural to assume that its appearance in the heavens and its motions have always been known to mankind. Its ruddy light naturally associated it in the Greek mind with the god of war, just as the soft, warm glow of Venus was considered appropriate to the goddess of love. To the Chaldean and other ancient stargazers, the motions of the planet were indeed of interest. No planet has received greater attention from astronomers, or has been used more for the solution of important astronomical and cosmical problems. Thus, it was from the observation of the passage of the moon in front of Mars, or what is termed by astronomers an occultation of the planet, that Aristotle concluded that the planets were more distant than the sun and moon. What reason he had for including the sun is difficult to conceive, as an occultation of that body would be quite impossible. Later, it was from the study of the motions of the planet made for Tycho Brahe that Kepler was able to derive his great laws of planetary motion. By observing the great hourglass sea, or Syrtis Major, on Mars, Huygens, in 1659, noted the rotation of the planet on its axis, and from a measurement of the planet made its opposition Riker was able to obtain a reasonably accurate estimate of the distance of the Sun in 1673. 1783, Herschel had written, "The analogy between Mars and the Earth is perhaps by far the greatest in the whole solar system." For over a century, the development of this analogy has been one of the most important features of astronomy, especially in popular estimation. Today, with a wealth of scientific and observational data acquired during the last score of years, the question, although more fully and intelligently discussed, is as far from solution as ever. Mars revolves around the Sun in an orbit whose mean distance is 141,500,000 miles. But this orbit is so eccentric, amounting to 0.093, that the distance varies about 13 million miles. As this distance from the Sun is about 1/2 as far again as that of the Earth, the light and heat that Mars receives are only about 4/9 of the light and heat received by the Earth, an important consideration in discussing the possibility of life on its surface. The real diameter of Mars is about 4,200 miles, a figure correct within 20 miles, so that its surface is 23/100ths and its volume is 0.147 or 1/7 that of Earth. The mass of the planet, derived from observation of its satellites, is about 1/9.4 that of the Earth, so that its density is 0.73 and the attraction of gravity on its surface is 0.38 that of Earth. Mars reflects 0.26 of the light that it receives, which is just double that of Mercury. In Mars may be seen a striking difference between the superior and inferior planets, for the crescent phases of the latter are conspicuously absent. This is because the orbits of Mars and the other superior planets lie outside that of Earth. Consequently, such a planet never comes between the Earth and the Sun. At quadrature, a certain amount of the unilluminated portion is turned towards the Earth so that the planet appears like a moon 3 or 4 days from full with a distinctly gibbous appearance. Kepler suspected the existence of satellites from a somewhat cryptic utterance of Galileo's in regard to the triple Saturn. No particularly sound reasons were advanced for the existence of such satellites. Still, that they might be found is forcibly reflected in 18th century literature. In Gulliver's Travels, 1726, is the striking statement that an astronomer on the floating island of Laputa had discovered 2 tiny satellites of Mars. Dean Swift even advanced the extraordinary statement that one of these moons revolved around the planet in 10 hours, the approximate correctness of which will presently be apparent. Furthermore, Voltaire, in his Micromegas, published in 1752, and obviously modeled on Gulliver's Travels, also speaks to these small bodies. Although literature and imagination had preceded observation, astronomers could not detect any companions to the ruddy planet until August 11, 1877, when Professor Asaph Hall, using the 26-inch refractor of the U.S. Naval Observatory at Washington, which at the time of its construction in 1873 was the largest telescope in the world, studied the vicinity of Mars with unusual care. In 1877, it was at conjunction, so that conditions were favorable for an exhaustive inquiry. On August the 11th, Professor Hall detected a minute speck of light near the planet, and a few days later, August 16th, he ascertained positively that it was a satellite. On the following evening, a second body was discovered, bewilderingly rapid in its motion. Since that time, the 2 satellites have frequently observed at opposition even with much smaller instruments. On July 18, 1888, the large Lick telescope was able to reveal them with their brightness was about 1/8 at the time of their discovery. The names appropriately designated to the new satellites, Deimos and Phobos, Fear and Panic, were taken from the Iliad and represent the companions in the battle of the god of war. The satellites are very small, having diameters respectively of 6 and 7 miles, as photometrically measured at Harvard University soon after their discovery by Professor Pickering. Phobos, the inner, is larger and travels an elliptical orbit in 7 hours, 39 minutes, and 22 seconds at a distance of only 3,760 miles. Deimos, its companion, moves in a nearly circular orbit in 30 hours, 18 minutes, at a distance from the planet of 12,500 miles. It should be remembered in all discussions of the nature of the surface of the planet Mars and in developing theories based therein that astronomers must deal with the little disk which one every 15 years has a maximum of about 1/5000th the area of the full moon. When the nearest Earth Mars is at a distance of 35,500,000 miles and when observed by a telescope magnifying 1,000 times, it appears as only as large as the moon with an ordinary field glass, enlarging 6 or 7 times. In other words, Mars is brought to its distance of 35,500 miles. Hence it is difficult to distinguish minute details. Consequently, visual and photographic observation of Mars must be of the most refined character, for especially in the former there is opportunity for psychological or subjective phenomena to occur in connection with the observation. While it is neither rational nor scientific to deny what credible observers claim they have seen through the telescope in examining the planet, yet it must be recognized that visual observations are attended by necessary limitations and should be received in a spirit of caution rather than of enthusiasm. The mapping of Mars is no recent matter, for even in 1659 a rough sketch of the surface of the planet was made by Huygens, in which the V-shaped marking at the equator pointing to the north can be identified as the Syrtis Major. This was followed by rough sketches from time to time down to 1840, when Maedler first began a systematic charting of the planet. His map was followed in 1864 by Quasars, by Flammarions in 1876, and Green's in 1877. Drawings of various parts of the planet were made during these intervals, but were not combined into good charts. Observations made by Professor Lowell and his staff at the observatory in Flagstaff, Arizona, have had the study of this planet especially in view. The Lowell Observatory itself is situated 7,300 feet above the sea and contains an excellent 24-inch telescope with which it is claimed that the faintest stars shown on the chart made at the Lick Observatory with its 36 instrument are perfectly visible. The atmosphere is well adapted for telescopic work, so that Professor Lowell and his colleagues possess singular advantages over other observers. On the other hand, in many important respects, there has been a lack of corroboration of their observations. The surface of Mars, as seen in the telescope, is composed of two white polar caps which wane with the approach of summer, orange areas, which are supposed by Lowell and his followers to be deserts, and blue-green areas which change their hue to orange during the Martian autumn and winter and reassume their verdant tint in the spring. The planet is covered with a network of fine lines first discovered by Schiaparelli in 1877 and called by him canals, a designation by which they are still known. These canals connect the polar ice caps with the temperate and equatorial zones. According to Professor Lowell, they may be regarded as planetary irrigation ditches, which serve the purpose of leading the melting water of the poles to those desert regions which would still blossom if properly watered. The canals disappear with the approach of winter and creep down from the poles towards the equator in the summer, a phenomenon which long puzzled astronomers until Pickering ingeniously suggested that we see not the canals themselves, for they are much too narrow, but the vegetation which fringes their banks, which withers as the cold of winter descends, and which flourishes with the melting of the snows. It was Schiaparelli who also first announced the curious doubling of the canals in certain instances, an announcement which was at first received with derision, but which has since been confirmed by his disciple, Lowell, and the astronomers of the great observatories. This curious gemination has not been satisfactorily explained, although Professor Lowell attributes it part to vegetal causes. By opponents of his theory, the doubling is regarded as an optical illusion, which can hardly be the case because all and not certain of the canals would exhibit the phenomenon. Furthermore, there is some photographic evidence offered by Mr. Lampland of Professor Lowell's staff that both the canals and their doubling are real. End of section 22.
Section 23 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Pamela Nagami. The Science History of the Universe, Volume 1. Edited by Francis Rolt Wheeler. Astronomy. Chapter 15, Part 2. Mars. The visual observations of Professor Lowell have been undertaken with great thoroughness and have brought to light such material which he has employed in the development of his theories. To do justice to his work in a single chapter is manifestly impossible. It will be most satisfactory to the reader to recapitulate in Professor Lowell's own words, derived from his work on Mars and its canals, the fundamental facts which he has recorded and on which he bases his conclusions. They are as follows, quote, Number 1. Mars turns on its axis in 24 hours, 37 minutes, 22.65 seconds with reference to the stars, and in 24 hours, 39 minutes, 35 seconds as a mean with regard to the sun. Its day, therefore, is only about 40 minutes longer than ours. Number 2. Its axis is tilted to the plane of its orbit by about 23 degrees 59 minutes. Most recent determinations of 1905. This gives the planet's seasons almost the counterpart of our own in character, but in length nearly double ours. For number 3, its year consists of 687 of our days, 669 of its own. Number 4, polar caps are plainly visible, which melt in the Martian summer to form again in the Martian winter, thus implying the presence of a substance deposited by cold. Number 5, as the polar caps melt, they are bordered by a blue belt, which retreats with them. This excludes the possibility of their being formed of carbon dioxide, and shows that of all the substances we know, the material composing them must be water. Number 6. In the case of the southern cap, the blue belt has widenings in it in places. These occur where the blue-green areas bordering upon the polar cap are largest. Number 7. The extensive shrinkage of the polar snows shows their quality to be inconsiderable and points to scanty deposition due to dearth of water. Number 8. The melting takes place locally after the same general order and method, Martian year after year, both in the South Cap. Number 9. And in the North one. This is evidenced by the recurrence of rifts in the same places annually in each. The water thus let loose can therefore be locally counted on. Number 10. That the South Polar Cap is given to greater extremes than the North one implies again, in view of the eccentricity of the orbit and the tilt of the axis, that deposition in both caps is light. Number 11. The polar seas at the edges of the caps being temporary affairs, the water from them must be fresh. Number 12. The melting of the caps on the one hand and their reforming on the other affirm the presence of water vapor in the Martian atmosphere of whatever else that air consists. Number 13. Since water vapor is present, of which the molecular weight is 18, it follows from the kinetic theory of gases that nitrogen, oxygen, and carbonic acid of molecular weights 28, 32, and 38 respectively are probably there too, owing to being heavier. Number 14. The limb light bears testimony to this atmosphere. 15. The planet's low albedo points to a density for the atmosphere very much less than our own. Number 16. The apparent evidence of a twilight goes to affirm this. Number 17. Permanent markings show upon the disk, proving that the surface itself is visible. Number 18. Outside of the polar cap, the surface is divided into red ochre and blue-green regions. The red ochre stretches have the same appearance as our deserts seen from afar. Number 19. And behave as such, being but little affected by change. Number 20. The blue-green areas were once thought to be seas, but they cannot be such because they change in tint according to the Martian season, and the area and the amount of the lightning is not offset at the time by corresponding darkening elsewhere. Number 21. Nor by any augmentation of the other polar cap or precipitation into cloud. It cannot, therefore, be due to shifts of substance. Number 22. Furthermore, they are all seamed by lines and spots darker than themselves, which are permanent in place, so that there can be no bodies of water on the planet. Number 23. On the other hand, their color, blue-green, is that of vegetation. This regularly fades out, as vegetation would, to ochre for the most part, but in places changes to a chocolate brown. Number 24. The change that comes over them is seasonal in period, as that of vegetation would be. Number 25. Each hemisphere undergoes this metamorphosis in turn. Number 26. That it is recurrent is again proof positive of an atmosphere. Number 27. The changes are metabolic, since those in one direction are later reversed to a restoration of the original status. Anabolic as well as catabolic processes thus go on there. That is, growth as well as decay takes place. This proves them of vegetal origin. Number 28. The existence of vegetation shows that carbonic acid, oxygen, and undoubtedly nitrogen are present in the Martian atmosphere, since plants give out oxygen and take in carbonic acid. Number 29. The changes in the dark areas follow upon the melting of the polar caps, not occurring until after that melting is underway. Number 30. And not immediately then, but only after the lapse of a certain time. Number 31. Though not seas now, from their look, the dark areas suggest old sea bottoms, and when on the terminator appear as depressions, whether because really at a lower level or because of less illumination is not certain. Number 32. That they are now the parts of the planet to support vegetation hints the same past office, as water would naturally drain into them. That such a metamorphosis should occur with planetary aging is in keeping with the kinetic theory of gases. Number 33. Terminator observations prove conclusively that there are no mountains on Mars, but that the surface is surprisingly flat. Number 34. But they do reveal clouds, which are usually rare and are often, if not always, dust storms. Number 35. White spots are occasionally visible, lasting unchanged for weeks in the tropic and temperate regions, showing that the climate is apparently cold. Number 36. But at the same time proving that most of the surface has a temperature above the freezing point. Number 37. In winter, the temperate zones are more or less covered by a whitish veil, which may be hoarfrost or may be cloud. Number 38. A spring haze surrounds the north polar cap during the weeks that follow its most extensive melting. Number 39. Otherwise, the Martian sky is perfectly clear, like that of a dry desert land. End quote. These facts, according to Professor Lowell, make reasonably evident on Mars the presence of, quote, number 1, days and seasons substantially like our own. Number 2, an atmosphere containing water vapor, carbonic acid, and oxygen. Number 3, water in great scarcity. Number 4, a temperature colder than ours but above the Fahrenheit freezing point, except in winter and in the extreme polar regions. Number 5, vegetation. End quote. While all of Professor Lowell's observations and results are not accepted by all astronomers, and there is considerable opposition to his conclusions, nevertheless, they are of interest and worth stating as representing this aspect of the matter in his own words. Comparative studies of lunar and Martian spectra made on the summit of Mount Whitney in September 1909 by Campbell of the Lick Observatory seemed to preclude the possibility of much water on Mars. Campbell's photographs show that the Martian atmosphere is no richer in water than the Moon's, which, if true, summarily disposes of Martian life. Slipher of Lowell's staff claims to have obtained ample spectroscopic evidence of water. The following paragraphs, taken from the concluding chapter of Lowell's book on Mars and its canals, may be said fairly to sum up his views on Martian life. Quote, that Mars is inhabited by beings of some sort or other, we may consider as certain as it is uncertain what these beings may be. The theory of the existence of intelligent life on Mars may be likened to the atomic theory in chemistry, in that in both we are led to the belief in units which we are alike unable to define. Both theories explain the facts in their respective fields, and are the only theories that do, while as to what an atom may resemble we know as little as what a Martian may be like. But the behavior of chemic compounds points to the existence of atoms too small for us to see, and in the same way, the aspect and behavior of the Martian markings implies the action of agents too far away to be made out. One of the things that makes Mars of such transcendent interest to man is the foresight it affords of the course earthly revolution is to pursue. On our own world, we are able to study only our present and our past. In Mars, we are able to glimpse in some sort our future. Different as the course of life on the two planets undoubtedly has been, the one helps, however imperfectly, to better understanding of the other. End quote. The views expressed by Professor Lowell in the work just quoted were further developed by him in the course of a few years succeeding its publication, and in Mars as the Abode of Life, published in 1908, he expresses himself even more firmly convinced that Mars is inhabited by a race of intelligent beings. Additional study of Martian phenomena, according to Professor Lowell, indicates that the canals and oases, as he sees them, are proof that life of no mean order of intelligence prevails on the planet. He suggests, quote, part and parcel of this information is the order of intelligence involved in the beings thus disclosed. Peculiarly impressive is the thought that life on another world should thus have made its presence known by its exercise of mind, that intelligence should thus mutely communicate its existence to us across the far stretches of space, itself remaining hid, appeals to all that is highest and most far-reaching in man himself. More satisfactory than strange this, for in no other way could the habitation of the planet have been revealed. It simply shows again the supremacy of mind. Men live after they are dead by what they have written while they are alive, and the inhabitants of a planet tell of themselves across space, as do individuals athwart time, by the same imprinting of their mind." End quote. To this he adds the statement that conditions for life on the planet are approaching an end, as it is rapidly drying up, and that the energies of the inhabitants are being the slowly diminishing supply of water. Quote, "The drying up of the planet is certain to proceed until its surface can support no life at all." End quote. So that as compared with the Earth, Mars presents a distinctly later period of evolution. No such danger at present confronts our own planet, but assuming that these explanations are correct, it is not improbable that the cooperative action of all the nations of the world may be required at some future date to deal with a similar problem. In opposing the idea of canals on the surface of Mars, much stress has been laid on the alleged fact that the finer markings and some of the apparent doublings are based upon optical illusions or psychological phenomena. Thus, to prove that instinctively the eye would arrange in the form of straight lines vague suggestions of markings, E.W. Maunder of the Greenwich Observatory, England, and J.E. Evans of the Royal Hospital School at Greenwich in 1902 performed an experiment with a number of schoolboys. A circular disc was exhibited 5 or 6 inches in diameter, on which were represented with some accuracy the shaded area of the planet as it might appear in the telescope. Instead of canals, a few faint wavy lines and a larger number of faint dots were inserted promiscuously. The boys were told to fill in with pencil on small circles on sheets of paper the details of the object exhibited to them, exercising as much care as possible. The object of the experiment was not communicated to the boys. None of them had any idea of the nature of the planet's surface. The result was that boys at the greatest distance from the object, where the faint lines and dots were just beyond the limits of separate visibility, drew canals remarkably like those noted by the telescopic observers of the planet. Hence, it was supposed that the eye in some way integrated such faint stimuli as irregular scattered dots and faint wavy lines into straight lines which have no objective existence. Much has been made of this test, but it may hardly be called conclusive, for Flammarion, when repeating the experiment with French boys, was unable to secure in their sketches lines resembling canals. Moreover, photographs taken during the opposition of 1905 at Flagstaff bring out a large number of the more prominent canals as straight lines. It is possible that psychology plays an important part, and Professor Andrew Ellicott Douglas of the University of Arizona, who has had opportunities to observe the planet at several favorable oppositions, believes the subjective phenomena have much to do with Martian observations. He says, quote, "One may confidently say that such realities do exist, but with the very faint canals, whose numbers reach occasionally well into the hundreds, discordance reigns supreme, and it is frequently found that different drawings by the same artist antagonize each other across the page." Considerations along these lines led me to study seriously the origin of these inconsistent faint canals by the methods of experimental psychology, and the application of these methods has resulted in a new optical illusion and new adaptations of old and well-known phenomena. End quote. The most important of these phenomena was the halo effect, where secondary images are produced under unusual conditions, which images affect the minute details of the surface. Professor Douglas also found that the irregular refraction of the eye produced apparent rays as from a small spot, which could be obviated in part by changing the position of the observer's head. Quote, "The ray illusion," he says, "is to me a very satisfactory explanation of many faint canals radiating from those small spots on Mars called lakes or oases. The only objective reality in such cases is the spot from which they start." End quote. Referring again to the halo, he reaches the conclusion that, quote, "The halo with its light area and secondary images accounts for details which have no objective reality, such as bright limbs of definite width, canals paralleling the limb or dark areas, numerous light margins along dark areas and light areas in the midst of dark, abundantly exemplified in Schiaparelli's map of 1881 and 1882. Professor Lowell, it must be said, has the unique advantage, or misfortune it may be, to see canal-like markings that are not visible to other astronomers. Thus on Venus he saw bands or lines which he considered bore a superficial resemblance to the canals of Mars and were apparently permanent and not due to clouds. Again, he claims to have seen lines resembling canals on the third satellite of Jupiter, which others have failed to recognize. Hence, many astronomers believe that he is predisposed to see such phenomena. Furthermore, canal-like appearances have been noted on the surface of the Moon by Professor W. H. Pickering as radiating from the central peaks of the northwestern slopes of the central mountain range of the crater of Eratosthenes. He observed two canals which in a small telescope appear straight, yet when seen with a large glass present considerable irregularity of structure. Other and new branches or canals were also seen. In various parts of the same crater, but especially in the southeastern and northern portions, numerous small canals and lakes present themselves. These markings are practically identical in appearance with those seen upon the planet Mars. They are too small to be well shown on photographs and seem to be of much more regular structure than the larger markings, which are also called canals. It is possible that this difference is due merely to the fact that the larger markings are better seen. There can be no free water on the Moon's surface, hence any canals with flowing water are quite out of the question. Yet the appearance is vouched for as remarkably similar to that on Mars by an observer who knows the surfaces of both bodies. End of section 23.